Welcome back for part 4 of the quest. That's funny. The session counter. Oh, it just took back down again. Briefly said 4 hours, as if lunch never happened. A terrible state of affairs. Oh, I just had my lunch and I'm back and I'm ready for some Gawar extensions. This is the good bit. This is what we came for. We're looking for the Quintic. The Quintic is hiding in, not this section actually, or section 5. It's in a couple of chapters time, but this is the theory that we're going to need. So, excited to jump into this and get going with some Gawar theory. Let's get going, I think. Just like this morning, I'm going to try and skip all the proofs unless I get distracted, and focus on just trying to get an overview of the theory, so that later when I'm going through, I have more of an understanding about how things link together, how those field extensions that we saw yesterday were really useful this morning, and how later on all those concepts that we looked at this morning about separable splitting, normal, things like that are going to be relevant this afternoon for Gawar theory. Okay, let's start reading through then. So, field extension, and this is given the name iota, which is again a very odd variable, but never mind. K into L is called a Gawar extension, so it has to be a sort of field extension if, and now this means that L, this is the, right, okay, this is the invariance. So the set of invariants of L under the automorphisms of L that preserve K. Ugh. Right, okay. Lots to break down here, lots to unpack. So we've got L over K, and we've got automorphisms that preserve the K structure of L. So these are automorphisms preserving K structure, kind of K properties and stuff. And then we've got L to the that is then elements of L fixed by all those automorphisms. So you do automorphism, you shuffle things around, some stuff's fixed by all of those automorphisms that preserve the K structure. In that case, call it a Gawar extension if that is equal to just K. Precisely K, or I of K, which we might call K. Alright. So first up, why would the elements of K be fixed, right? Why would K be in this at all? Can I think of any Gawar extensions, right? There'll be some examples coming, I'm sure. Our simple extensions, Gawar extensions, for example. So the automorphisms, like I was imagining for C, I goes to minus I, that does preserve the real numbers. Those are all fixed. And in fact, those are the only things that are fixed under that particular isomer, or that particular automorphism. So maybe that's a Gawar extension. Okay. Gosh, so by theorem 3.18, a finite field extension is a Gawar extension if and only if L is the splitting field of a separable polynomial over K, and if and only if it is normal and separable. This was theorem 3.18 was the big one with 3 equivalent things, wasn't it? Yeah, down here. So the automorphism is finite. The following statements. Here's the thing. This is definition. This is in the definition of a Gawar extension. So I now see what the point of this was, right? Because there's some other things that. So this great example. This morning, when I looked at this, I thought, oh my goodness, look at all this subscript, superscripts, and now I find out that's what Gawar was interested in, and now I'm interested too. So these things being equivalent gives me other ways, other things that are equivalent to the definition of a Gawar extension over here. Okay, so finite field extension. So 3.8 is now key. I had loads of stuff going on in there, but hey. 3.18 is key to understanding this. So Galois extension, if and only if L is the splitting field of a separable polynomial, and if and only if the other one is normal and separable. From this we see that L of K is finite Galois extension, which is the composition of two extensions, L of K1. Oh, sorry, we see that if L of K is a finite Galois extension, which is the composition of two extensions, then that's also a finite Galois extension. It's not true in general that K1 over K is then also a Galois extension. Ooh, the top one's a finite Galois extension, but the bottom one might not be. So we've got L over K, L over K1, K1 over K. So finite goes through because of the tower law, right? If L over K is finite, then these things are both finite. I've got the Galois extension, which is the composition of two extensions. Oh gosh, it's about being, so Galois means normal and separable. Normal and separable, and that's something to do with the minimal polynomials in K1 versus in K. No, wait, but that one is finite Galois extension. This one might not be. So K1 might not be separable, or it might not be normal. C in 3, theorem 4.4, I guess. If L over K is a Galois extension, we write this. We call it Gal L over K, and we also call it gamma L over K, which is, I guess, the Greek letter G for the Galois extension. And we're going to call the automorphisms of K over L. I'd like some better notation for that. Gamma for the automorphisms of L that preserve the K structure. That is gamma. I wonder if we're using Gal. It looks like, looking down at the bottom of this bit of paper, it looks like Gal is going to be the language we use today. Okay, so that's a notation thing. The Galois extension, no, the Galois group. Oh, because it's a finite group of automorphisms. Oh gosh, okay. Gal of L over K equals aut K L finite, kind of finite, maybe finite group of automorphisms. If the degree is finite, then it's, well, that's the degree of the group. Wait, so that Galois group of automorphisms. Wait, we know for C over R. Hey, remember this fifth. We've moved on to Galois stuff, which looks very different, right? There's a lot of different notation. It's a little bit scary, but it's coming together. After lunch, it's coming together. We're going to make it work. We're pushing a boulder up a different hill today. Or is it an extension of the existing hill? Tell me more about that size of the group thing, because, not you, sorry, the notes. I want the notes to tell me more about the size. Splitting field for a separable polynomial of K. So the number of automorphisms is the degree. So that automorphism group for the complex numbers over R, that has degree 2. So the splitting field is C2, the group with 2 elements. It really is just complex conjugation. I think we now know enough to know that's the only automorphism of the complex numbers. If you're joining us on the quest today, make sure to stay hydrated. I've got a cup of tea this afternoon. And I'm trying to learn about Galois extensions. Really, it's crystallizing for me because it's giving kind of Galois names to things that we were trudging around with this morning. Okay, if L over K is finite, then it's a finite group. Oh, brilliant. Okay, let K be a field, and let P be something, a separable polynomial. L over K be a splitting field of P, which will sometimes write Gal P for the Galois group associated with that polynomial. Yeah, the various splitting fields are not related to I don't really know what a canonical isomorphism is, I'm afraid. Stricto sensu. Is that Latin? Are we learning stricto sensu? Stricto sensu. Unadapted borrowing from Latin in a tight sense. These notes are so cool. In a narrow or strict sense. In a strict sense. We've also switched to a different set of notes. So yesterday was rings. Today, different author for the notes here. Damien has written some notes with Latin in. Good stuff. Can only refer to an isomorphism class of finite groups. Oh gosh, not a particular group. Quest for the dictionary. Yeah, learning, right? Learning Latin of all things. Stricto sensu. Stricto sensu. I like it because it sounds just like saying in a strict sense, but with vowels at the end of the words. In a stricto sensu, that can only refer to an isomorphism class of finite groups. Fundamental theorem of Galois theory, to be proven later. The map going from subfields of L containing probably sort of K, we go from subfields of L contain K, goes to subgroups of the Galois group. The Galois group. That's a cool phrase. So given by that is a bijection. I guess your subfield might contain some of the roots or whatever, and then your subgroup can permute some of them. We'll see later. There's an example here, and then I think I need to take some notes. I'm reading and taking notes today. Didn't take enough notes yesterday. We shall compute the Galois group of the extension Q root 2I over Q. I think it's going to be 4. And of its subfields. Okay. Note the Q root 2I is the splitting field of the polynomial that. Good. It's the splitting field because it's the field over which that splits. You need to go to this field in order to get all the roots. Yep. Thus is the splitting field of a separable polynomial, and thus Galois. The splitting field of a separable polynomial. That's one of the things in theorem 3.18. The splitting field of a separable polynomial. The splitting field of a separable polynomial. Okay, that's kind of part 2 of theorem 3.18. I've got to learn theorem 3.18. How to recognise Galois extensions. We've got about 3 equivalent definitions, which is a normal place to be in for some important definitions in maths. So you've got like 3 equivalent things, and that kind of means that once you've proved those 3 definitions are the same, and you meet a new thing, you can prove it's an example by using any of those 3 definitions. And it feels quite weird having different definitions, but if you prove they're equivalent, then it's fine. Right, successive extensions. Bring me the tower law. Minimal polynomial of if this is irreducible, yeah, typically no root in Q. Similarly, polynomial of x squared, no root of this, and it's I, yeah, no root in that, since that's in R. Tower law, I called it. Maybe I saw it, I don't know. And the note after proposition 3.9, 2.2 is 4. What was the note after proposition 3.9? Come back to page 21, but what was the note after 3.9? Oh, yeah, it's about the degree of the polynomial. Good. That's what we wanted it to be. 2 times 2 is 4. Welcome to the quest. Deduce from theorem 3.17 that the size of this Galois group is 4. Let G be that Galois group. From the classification of finite simple groups, we shall come back to this later in the course. Conclude that G is abelian. And now I'm starting to think that maybe I should have studied the classification of finite groups from the rings and modules notes. That is exciting. We'll come back to it. What should I study first? Maths advice in chat. An exam about quadratic equations. You'll do factoring and square roots starting tomorrow. Okay. Some equations have long solutions and it makes me doubt my answers. Do you know the quadratic formula? I can't remember how ninth grade works. If you know the quadratic formula, then just go in with full confidence because you can solve all of these things. If you're factorising things, then sometimes it's long because you've got to check lots of possibilities, but if it's all whole numbers, you never have to check that many possibilities. If it's rationals, then it factorises over Z as well. I don't know which theorems you've got. I probably know the quadratic formula. It's just sort of strictly better than the thing where just a side note. People can skip forward in the VOD if they want to. If you try to solve like this, then there's kind of two ways to do this. If you want to factor it, you can think of the numbers, but instead of thinking of the numbers, you can just get out the quadratic formula, which says that you should do this. And these numbers are your roots. They're the roots of the equation. So I should just work out what these are and plug them in over here. And this is 4 plus or minus root 2 over 2, which is 1 or 3. So I should take away 1 and take away 3 for the roots. Once you know the quadratic formula, then it's all fine. The zero theorem. Is that the factor theorem? I think that's the factor theorem, which we've had a couple of times in this live stream, weirdly. To say that if P of X is 0, sorry, if P of A is 0, then P of X is X minus A times some Q of X. That one? Worth knowing. Helps you bring out factors of polynomials. But formally it's just doing the thing that you want it to do. Yeah, that thing. This is doing the thing where, so you've got the quadratic formula for solving quadratics, but then a more complicated thing you might need to do is to solve some sort of cubic, where you might need to notice that x equals 1 is a root, and because it's a root, that means that x minus 1 is a factor. But in ninth grade, I expect you to just be like totally like flipping between the ideas of, oh, this is a root, this is a factor, because look, I can see that it's a root. Formally, there's some work to do to actually prove that those things are equivalent concepts. But in ninth grade, don't worry about that at all, right? You're just like, oh, brilliant, yeah. One is a root, so x minus 1 is a factor. Go for it. And it's worth knowing because then once you pull out the x minus 1, I'd hope you could do this kind of division stuff. You stand a chance of being able to factorise this further. Oh no, it's the polynomial x squared plus 1. That's got no real roots. What are we going to do? There is actually a cubic formula, but I don't think you should learn it. There's also a quartic formula, but I really don't think you can learn it. There's no quintic formula for 5th degree polynomials, and that's the name of the stream. We're going to try and prove that over the next week or something, if I ever get through these notes. Cool, right. That's the link between what you're doing and what I'm doing, by the way. Good. Yeah, you can mute me, and there's just some maths going on around as well. I unlock custom emotes if we get a certain number of viewers total, I think, then I unlock custom emotes, which I'm very excited about. If we can do that by the end of the week, that'd be great. I might be taking Twitch too seriously, or not seriously enough. Let's find out. Okay. Where are we going? Classification of finite groups. G is abelian, and that's very exciting because there aren't that many groups of order 4. There we go, that's the group stuff. Further from the structure theorem for finite abelian groups. Yeah, okay, fine, we definitely need this rings and modules thing, maybe. There are two possibilities. 4z, z by 4z, or the Klein 4 group. Now note that we have this thing. The extension of this over Qi is 2 follows from the fact that the extension is not trivial, otherwise it would be equal to 2 by the Taylor law. I love the Taylor law. Similarly, this thing over root 2 is 2. Because the only group of order 2 is 2, we conclude that this thing is that, and so this thing is this. Oh, so we've got a group. I guess what I want to know is, like in the power law thing, if you have m over L, L over K, and you work out the Galois groups for these things, do you just cross them together to get m over K? I sort of hope so. I could probably work that out, but not right now. Oh gosh, we're still going. Fundamental theorem, it cannot coincide because they correspond to different subfields of Q root 2I. Thus we conclude that G has two distinct subgroups of order. It's gone very group theory suddenly, which is brilliant. The elves, the forest full of elves. People don't know what I'm talking about, but I have this map where, anyway, so it must be this one. Ooh, there are different subgroups. Right, okay, so it's like, so you've got Q or something, and then you put root 2 in it, and you put I in it, and you put root 2 and I in there. And then these things, I think you could draw these like arrows for like how you're going to add stuff, and then you get these kind of like Galois groups for each of these field extensions, and they're kind of subgroups, normal subgroups, maybe just subgroups. I'm getting there. Maybe when they say subgroups, they just kind of, my intuition is that normal subgroups should be the thing that we're talking about here. Altogether, this has 3 non-trivial subgroups. Yep, that, and the subject subgroup generated by 1, 1. 3 non-trivial subfields. Any field of characteristic 0 contains Q. Don't worry about that. Fine, okay. It says not to worry about it. I've already found 2 of them. Third subfield is given by Q of I root 2. I don't know where to put this on my chart. Let's put a drawing in here. Fine. I root 2. Oh man. And those things are not equal. This completes the description of the Galois correspondence for Q root 2I over Q. Here are some field extensions which are not Galois. So that thing's not normal, so it's not Galois. Oh. So if you thought this was just roots of polynomials, then nope. Maybe that's good, because if you could just always throw in roots of polynomials, then we would be describing all the quintics as well. We want to say something about. Okay, so we're going to distinguish here somehow. This thing's not normal, so it's not a Galois extension. And then there's a complicated one there. This is not separable. It needs to be normal and separable to be Galois. Normal and separable to be Galois. Oh, good times. We got some Galois theory going down. Galois theory is about group theory, which is exciting because I've been waiting for the groups to properly turn up. Excuse me. Here are some groups. Okay. Galois extension is normal and separable. What do I want? This definition seems like the worst one. Okay, because I can't read it. Let's just write down one of the other ones, right? That's my note on what a Galois extension is. Quest log. Galois extension is normal and separable. And then equivalently in here, it's the splitting field, splitting extension for a separable polynomial. I think, double check. Just trying to quote this bit. Is the splitting field of a separable polynomial over K, and if and only if it's normal and separable. Okay, good. From this we see that, okay. Good, end of lecture 6, apparently. Okay, and I want the Galois group in my notes as well. automorphisms preserving the K structure of L so down here, if L extension over K is Galois, then the Galois group gal of L over K is, right here, it's the automorphisms that preserve the K structure on L. And there's only finitely many of them. It works nicely with degree. Okay. We're going to prove that subgroups have something to do with subfields. We haven't proved it, we have had a look at a kind of Galois extension down here. Okay, we've got some field extensions which are not Galois. Good, right, okay. I'm ready to have a quick look at Artin's lemma, I think. 4.2. Basic statement, which is a linchpin of the whole theory. I wish they wouldn't call things basic, but you know, especially if you're going to give me the automorphism of rings, automorphism preserving rings. Let K be a field, and let G be some of the automorphisms of K. So finite subgroup of those automorphisms. Take a finite subgroup. Then the extension up to from, no, wait. The extension up to K for any field. We are very general here. There's no like normal separable. The extension from the things fixed by G all the way up to K is a finite Galois extension. And the inclusion, G goes to the automorphism, gosh, preserving that thing, preserving the KG structure on K is an isomorphism of groups. So it's a way of constructing a finite Galois extension, maybe? Why is it a basic statement? I mean, it is basic in the sense that it's not using any of the advanced normal separable stuff that we had further on. So I'm going to interpret basic not to mean easy. The key point of Artin's lemma is the fact that that's a finite extension. Oh gosh, yeah, I missed the word finite. The inclusion, G is in the automorphisms of K under the KG structure. Key point is that it's a finite extension. Well, let's just go through it slowly. Proven in lemma 4.3 below. Right, lemma 4.3. Let K be a field, and let G in this automorphisms of K fixing the ring structure be a finite subgroup. So that's this G up here. Then the degree of K over things fixed by G in K is less than or equal to the size of G. The degree of that field extension, K over K of G, suppose not, is the case to proof. Then there's a sequence of elements linearly independent over Kg and such that there's more of them than the size of G. Say there's n of them. No, call the size G n now, okay. And let the first n of them be an enumeration of the elements of G. Oh no, sorry, take those as the elements of G. Consider the matrix. Consider the matrix. From your group elements, look at what's happening to each of those elements in K. Oh my goodness, so you look at your permutation. So these are going to return elements of K. So this matrix has got elements of K in it. The columns are linearly dependent over K. Oh, I see. We're going to N. It's a rectangular matrix. We're going N in this direction, and we're going D in this direction. The columns are linearly dependent over K because there's loads of columns. So there exists a sequence which sums to 0 linear algebra, brill. And then, okay, so that's a sum of the, we're summing over I, summing sigma k, where at least one beta I does not vanish, such that you can take a linear combination of the columns. I'm struggling with the sigma k's here. Is this for all k or something? Or yep, for all k, good. Page turn. Always getting caught by the page turns. For all k. Such that the linear combination of these elements is 0. You add the column vectors together and you get the 0 vector. I kind of wish this was vector notation. Never mind. Choose the sequence so that the quantity R is the number of. Choose the sequence 1 up to D so that the quantity is minimal. Okay. Let them cook. Exists a sequence of betas for all k. Okay. For all k, find some betas. Now choose the sequence so that the quantity number of non-zero ones is minimal. Okay, count non-zero elements. And I want fewest non-zero elements. Renumbering, we may suppose, okay, permute the columns, and there's a whole bunch that are 0. Dividing by BR, fine, okay. Now note, by the assumption that these are linearly dependent over kg, there exists an I0 in there such that this thing is not fixed. Gosh. Linearly dependent over that. Since, particularly, we must have R bigger than 1, since I0 is not R. I0, a sort of first one, such that beta I0 is not fixed. Why can it be in kg? Why would beta be in the kg thing? Beta's just a number, right? Beta's a ring. Beta's now the ring. We're doing ring algebra, James. I think the betas belong in the K, in the field. We're doing field algebra, James. Okay. At least one of them's not in there. The dimension of that thing, things that are fixed by all elements of G, not too big? No. I0 is not the last one or something. Renumbering again, assume that B1 is not in kg. Now let k0 be such that, oh my goodness, it's that element which doesn't fix it. Oh gosh, things that are not in the fix. Right, okay, so there's an element that's not equal to beta 1. Applying sigma naught to the equation. This is very spicy. Right, okay. And then that's equal to, so that's equal to that. And then this thing, sigma k of alpha I, in other words, gosh, why does this match up? I'm really struggling with these. Sigma k naught applied here. You asked about music. Sorry, I missed your music question. What do I listen to? I do motivational. I think I go quite high energy. Not on the stream because I'll get muted if I put the stream on. I think you're muted, so I'm going to go. I go high energy, but that's me. Keeps me going. Why is this not happening? Why has this gone away? Oh right, okay, good. We're still here. We're still, sadly, we're still going. subtracting the equations, there's something cool going on, and then this is equivalent to writing that BR has worn this. Oh my goodness, sort of linear algebra stuff. This contradicts the minimality of R. You can make another one of them be 0. Cannot have D being there, which is what we wanted to prove. That's really complicated. I don't really understand any of the linear algebra that's happening. Oh well. Position to prove Artin's lemma. First prove that this thing, K is G. Okay, gosh. There's only 4 lines. How hard can it be? I'm going to skim it and come back later. It's my standard. My standards for today. The bar is low. Okay. So things that are fixed by G are definitely fixed by. Oh my goodness. Definitely fixed by things which are fixed by. I think these brackets are just for convenience. I hope. Automorphisms of Kg of K. Oh, there's just too many automorphisms. Automorphisms that preserve the Kg structure of K. Those automorphisms preserve the Kg structure, so probably preserve Kg, so probably preserve K? No, well, preserve Kg. Okay, so the automorphism of an automorphism, maybe that's supposed to be the fix or something. No. So I'm going to put a little exclamation mark for understanding aut, like S of K. I'm not sure I understand. I've been saying preserve the structure, but I'm not certain I remember what that means. On the other hand, we have G in the automorphism group by definition. So the other way around. Okay. Now, since that's a finite extension, by lemma 4.3, anything to do with the finite extension? Gosh, it's less than equal to the size of the group. Since this is a finite extension, we can conclude from ages ago that K over Kg is a splitting extension of a separable polynomial. With coefficients in Kg. Gosh, 3.18 was so important and so difficult. We must thus conclude from 3.17 that the size of the degree is the number of automorphisms. On the other hand, we know that the degree is less than or equal to G, so the number of automorphisms is less than the size of G. Since G is in the automorphism of K that fixed Kg or something, we also have size of G is less than or equal to automorphism size. So we conclude that the size of G is the size of the automorphism. This implies that G is equal to the automorphism group. Have different groups the same size, so there's something else going on there. Theorem 3.18 implies that G of GK is a finite Galois extension with Galois group G. Extension K of Kg is a finite Galois extension. Isomorphism of groups. And we know from 4.3 that this thing, size of the group is equal to the size of the automorphism thing over here. I don't think I've understood this automorphism subscript K superscript G. That's probably the thing that I've got to get a handle on. Theorem 3.18 implies that that's a finite Galois extension with Galois group G. Oh, is it G? Is she kind of in that? Yeah, G is in. Right, this thing. That's what the more that's going on. G is actually in the automorphism group. Why is G in there? Quickly. So, automorphisms of K. Good times. I have no idea. I have not understood that subscript thing. I might go back and understand the subscript thing. Before it was automorphism with subscript sets or something, and now it's automorphism or rings. G is an automorphism of rings of K. inclusion into that automorphism kg. An isomorphism of groups. Yes, I think I want to look out for more automorphism subscript L of K stuff. Subscript K of L probably. This is the exclamation mark thing. When that thing down there is also a field. I don't really know what I'm doing. This is what I'd like to understand. Is there one of those in the definition of a Galois extension? Not paying enough attention along here. Yeah, automorphism K of L. That's precisely the thing in the Galois extension. To do more of them in here. 3.18. 3.98 have one of these in as well. 3.17 have one of those. These were all the way through this morning and I completely missed understanding what they were. Did I get too excited about automorphisms turning up in the first place? Splitting fields. Separate polynomial K. Splitting field of a separate polynomial K. Automorphisms with a subscript K over L. Yep, that's what I want to understand. Back to find some automorphisms. Okay, we're going to have to look out for them, I think. No automorphism. Ah, right, hang on, that was it. That was it. M over K is a field extension which write or Km for the group of bijective maps of K extensions from M to M. Bijective maps of K extensions, the group laws constant maps. In other words, that is the subgroup of the automorphism ring automorphism compatible with the K extension structure of M. Compatible with, so here I need to be imagining compatible with the KG subset. KG, I've got to get one more time down here. Down here somewhere, there's the K to the G, which really, just to be really clear, is the invariance. I have to go so far back to find that. Might never find it. All the way to back here. I've gone all the way back to the preamble. I've gone too far. Right, okay, back in. Things that preserve that structure. Okay. So G is actually that automorphism kg of K. So this is automorphisms over of K that kind of preserve the kg. Respect that, which I guess means, does that just mean respect, keep it fixed? In particular, where's your unit? Where's 1? I kind of feel like it's in K. Whenever we do these field extensions, that your unit's in both fields, right? So, proof. Unit of the big field. Unit of the big field works as a unit for everything in the small field. Nothing else does, so your unit better be in the small field. So, okay, shared unit. And now, if we're talking about automorphisms that preserve the subscript field structure, it's going to preserve the copy of that structure, right? 1's going to go to 1. I think I need to practice a bit more with some automorphisms, but I think it's going to preserving the kg structure. I think means, in particular, it includes keeping the kg, that kind of image of kg that lives inside K, very literally lives inside K, is preserved by the automorphism. Not shuffled, just literally preserved. I mean, it is. It's a bit daft, really, because G, and then the thing we're proving is like, well, no, hang on, G is, by definition, K to the G is the things that are actually fixed by G. Okay. So, K is actually the automorphisms of this. Theorem 3.18 implies that that's a finite Galois extension with Galois group G. Okay. Not because of polynomials or normal inseparable. It must be that other definition that I kind of ignored about the inclusion map and what it is for a Galois extension in the first place. Back 4 pages, 3 pages. G to the ORT K. Yeah, so the automorphisms of this. So we're saying G is the Galois group for that extension. If it's the automorphisms of L over K. So down here somewhere, when we discover, aha, brilliant, G really is the automorphisms of K over Kg, that's why it really is the Galois group for that extension. What's Artem trying to do? I'll just say, given a group which is in that place, the extension over the invariance is a finite Galois extension. The inclusion is an isomorphism of groups. With Galois group G, right? Inclusion is an isomorphism. I don't really understand that language, I think. Let's go back in. G inside that automorphism of G of K is, yeah, it's an isomorphism of groups. Oh, hang on, those things are, for each of these is one of those. Those are the same. Right, hang on. So this is literally Galois group. Galois group. So it's kind of Galois group isomorphic to G, because the Galois group is actually the automorphisms, and G is like the automorphisms of K, and this is the automorphism. Anyway, this is literally the Galois group of K over Kg, and this is like, okay, once again being tripped over the difference between a thing and its isomorphic image. Fine. Yeah, these notes have got decimal points in the theorems and lemmas. Doesn't quite work like a decimal point. Like 3.18 comes after 3.17 and way after 3.9, which is quite disconcerting, right? They're not ordered like decimals. Some people really don't like this, and some people will even make the point, why not just use integers, right? It's not like we're going to run out of integers. So the lecture notes we were looking at yesterday, just numbered everything and kept going. I quite like that they just hit like comment 173, remark 174, and just keep going. We're not going to run out of integers. So this notation gives you, this idea of numbering gives you some idea about where it is in your notes, but so does theorem 129. Anyway, a kind of menu approach where you just number everything and then say, just pick one off the menu, it's fine. Good, okay. So, one more time through Artin's lemma, because I want to get it in my head. Artin's lemma, K is a field, and G, pick any finite subgroup you like. Then there is an extension. Okay, so I should start imagining an example, right? If I'm imagining C for my field, and GB some of the automorphisms over the reals of finite subgroup. Hang on, that stuff we had before actually. Let's think about the stuff before with the subgroup of where the automorphisms had order 4. Then the extension K over KG. This is the thing I wanted, right? K over the things that are invariant under K is a finite Galois extension, and the inclusion with Galois group G, more or less. That's an isomorphism, so I would probably write that they're isomorphic, I think. I hope that's allowed. Galois group G. Excuse me. Sorry. Slightly unwell, which doesn't help with the maths. Here we go. Rowan is 5th with like a reference, a 9th grader can use to study and learn. Textbooks, maybe a website. Oh gosh, what's in 9th grade? 14, 15, like roughly GCSE. Are you aware of BBC Bite Size? I quite like BBC Bite Size. So it's from the British Broadcasting Company, BBC, in the UK. If you search, hang on, let me just drop it in chat or something. Yeah, I'm going to drop it in chat. BBC bite size. I think that's equivalent to grade 9. Sorry if that's like a level below you or a level above you or something. I'm trying to do the conversion in my head. It's got like stuff about different subjects, including math. We'll find out. YouTube for GCSE, I'm also aware of Primrose Kitten, which I think is quite good. It's quite well thought of. If you're on GCSE, very popular with GCSE biology, actually, GCSE science. Let me link to that as well. Chemistry, maths and physics. Wait, do you do maths as well? I think so. GCSEs. Maths? Yeah, oh no, A-level maths. Let me find the right one. There you go. GCSE maths. Primrose Kitten's also pretty well thought of. Oh, I know there is a chemistry tutor guy, and Khan Academy's good. Yeah, those are classics. I'm giving a shout out here to the BBC, because I'm British, and Primrose Kitten, which is a decent website. I think have I met Primrose Kitten? Can't remember if I met Primrose Kitten. I've definitely seen Primrose Kitten speak at events and things. Yeah, impressive amount of content. Of high quality. There you go. That's recommendations. All recommendations are just that, they're just recommendations. Not an endorsement by, well, I guess who would it be an endorsement by? Groovy. Okay, I wanted a copy of Artin's lemma on my notes. Thinking about the way that this extends. Yeah, okay. Isomorphism of groups. Finite subgroup of the automorphisms. Okay, right, we're just going to have to write out some of this. Artin's lemma. Artin's lemma. What have we got then? We've got K a field, and we've got G a subgroup of the automorphisms as just any automorphisms you can find of K, a subgroup. Then there is a field extension, a Galois, a finite field Galois, finite extension. Let's get the words. There is a finite Galois, and then the extension K over kg. Oh, is there also a store? Let me look at that up in a second. Then the extension, then K over kg is a finite extension with Galois group G. I think it's a finite Galois extension, right? Back down again. Every time I reload it, every time I change docs, it goes back to the top of the page. Finite Galois extension, good. Right, so why have you told me Primrose Kitten is also a store? There's a free revision guide. Oh, they're charging for lots of things like masterclasses. I didn't realise, sorry. I knew that they had a free YouTube channel. Can you try and get to their YouTube channel instead? Sorry, I've linked you to some sort of store or something. Is the online course free maybe? I don't know. Yeah, sorry about that. Oh, they sell gift cards. Didn't realise they were charging £100 for a masterclass. I think that's fair enough, really, depending on what's in the masterclass. BBC Bite Size is free. Right, okay, you've got a YouTube channel. That's what I was trying to link you to. There's a YouTube channel with quite a lot of content on it. I didn't mean to just I wasn't trying to tell you to just buy a load of stuff off someone I met once. Which you're welcome to buy a load of stuff off someone I met once, but don't have to. What are we doing? We're trying to write Artin's lemma down. Finite Galois extension. I feel that's important. The inclusion is an isomorphism of groups. That's like a very complicated way of saying they're isomorphic. Finite Galois extension. Okay. That's kind of the way that you might build things together from like your chain of subgroups. Oh, I should really have learned the... We're going to have to go into module world, aren't we? I can feel it coming. We're going to have to go modules. Oh, I can just... Yeah, I can tell. And there's a lot of modules. Classification of finite abelian groups is... Well, maybe we'll need to know it in general, but... Yeah, okay, I suppose potentially we might need to understand the general classification of finite abelian groups, but if we're lucky, we only need to understand A5 for the Quintic, possibly. Maybe we only need to understand one abelian group, and that's much easier than understanding all abelian groups. Okay. Right, fundamental theorem of Galois theory. Here we go. Right, if you go from K to L as a field extension, I don't like that. Not certain I like this. I think I was preferring writing them like this, but fine, okay. And then I have K. Right, so it's like an inclusion thing. It's an injection. This arrow is really sort of surprising me. Anyway, field extension. I guess this lets you lay it out with a kind of arrow. Fine. Okay. Call a subfield of L containing IK an intermediate field. Subfield of L that contains, not quite K, but the image of K, fine. Let I be K to L be a finite Galois extension. Theorem. Here we go. Finite Galois extension. Galois means normal and separable. Okay, the map, subfields of L containing I of K to subgroups of Gal, given by M just goes over to Gal, is a bijection. Okay, so this is something about the structure of that field of L having something to do with the subgroups of the Galois group, which is exactly the sort of stuff that people say in quite a kind of general way, right? People are just like, oh, introduction to Galois theory will say something like, oh yeah, it's all about the symmetries of the roots, the symmetries got something to do with the symmetries of the roots of subgroups, A5 simple, anyway. Its inverse is given by the map H goes to the things fixed by H. These invariant sets that I dismissed earlier this morning are very important, aren't they? Its inverse is given by that map. It's amazing that's an inverse. H doesn't look like a map at all, does it? But H is a subgroup of Gal LK. Goes back to that's a subfield. That is a subfield of L. A subfield. So this should be a subfield. A subfield of L containing I of K. And these are things in L that are fixed by H, fixed by all elements of H. For a subfield, I mean, probably the action on the field is supposed to be preserve all the field stuff, so probably closed on the field operations, so it probably is a subfield, and it contains the image of K because the things in L that are fixed by all members of H, I kind of still feel like it's because it's preserving the identity and the K structure. Never mind. Okay, I should go and check that at some point. Because 1L and K structure? That's my kind of estimation of why this thing's true. Okay. Where H is a subgroup. We shall write G subgroup M to be the Galois group of L over M, where M is the name for one of our subfields, like an intermediate subfield, I guess. So precisely the thing that I wanted to be true, right? I've scribbled something vague at the top about normal subgroups, and this is kind of the precise version, I think. I think we're getting there. We're getting there. M be a subfield of L. Right, hang on, there's still more theorem. Part 2. A long theorem. Good. No, I've scrolled too far. Part 2. Let M be a subfield of L containing IK. We have. Brilliant. Size of LM is the number of that. Size of that is the number of those. Excellent. So they multiply up nicely. L over M over K. Brilliant. Let M be a subfield of L containing image of K. So are there subfields that don't contain that? Sure, just take like... I don't like the idea of a subfield that doesn't contain IK, but hey, fine. I guess there's nothing in the word subfield that means we're preserving field structure under all elements of the field, so not... It could be a field over a different... It's not like claiming we're a field extension over the same structure. It's just some field. Okay, then M over K as a Galois extension. Okay, fine. Okay, we're thinking about it as a Galois extension. But this one does contain IK. Good. It's a Galois extension, if and only if the group is a normal subgroup of Gal LK. Here we go. Nice. Something about normal subgroups. If that is the case, there's an isomorphism from quotient your Galois group with that normal subgroup to the Galois group M over K. Can go down into the structure of M over K, which is uniquely determined by the fact that the isomorphism for going down to M, gamma mod GM, gamma, oh gosh, vertical line M. Oh, it's so close. Is that gamma over M? No, that's gamma line M for any gamma. Oh, here, that is the restriction of gamma to M. Why am I restricting gamma? What was gamma? For any gamma in the Galois group. Gamma restricted to M just means... I don't like that, I can find it. The extension of L, so that's the Galois group of L over K includes loads of stuff. Gamma is the restriction where you just permute the elements in M. We'll just do the automorphisms, preserving the K structure over M. Good. And it's part of the statement that gamma M equals M. It's part of the statement that gamma M equals M. As an isomorphism, uniquely determined by the fact that mod GM. So many things going on at once. It's sort of so colourful. So little rich and various things going down. We finally got to a theorem which tells us something about the kind of normal subgroup way that these intermediate fields are structured. There's a structure thing going on. Okay. We're going to ignore the proof for now and focus on trying to get a version of this into the notes, trying to simplify this as things are going on. Okay, and this is going to be crucial. That the idea is that A5 doesn't have any non-trivial normal subgroups, so there's very little you can do in the way of intermediate fields. The normal subgroups of the smaller symmetry groups are probably... Excuse me. The normal subgroups of other groups are probably going to give us a way to structure. That's how we're going to build a quadratic formula. We're going to finally build a quadratic formula in a bit. Okay, can see something now. Theorem 4.4. Okay, how much of this do I want down? Map from subfields of L containing IK. Map from intermediate fields M. So we have K over L over K and M intermediate. Let's workshop this a little bit, which I'll remember means that it's a subfield that contains kind of K. And then there's a map from M goes to Galois L over M. It's a bijection. So I haven't given that map a name, but M goes to Galois if that is a bijection. And then part 2, M be a subfield of L containing K. I'll remember that again. We have the degree of L over M is the size of GM, where that's the Galois group of L over M. So I'm going to write that down again, sorry. Galois group of L over M, like that. And M over K is going to follow from that. You've got to remember those things multiply to give you the size of the Galois group L over K by the Tower law. And then part 3, M over K is Galois extension. Galois extension if and only if Gal LM normal subgroup. Okay, we're getting somewhere. We're getting somewhere. Okay, so what do I need? I need M intermediate field. We've got KLM. M's an intermediate field in this theorem. Okay, send it to subgroups. Send it to the subgroup. Send it to the subgroup. Take your field and show me the subgroup. This subgroup, the Galois things, messing around with L as an extension of M. Kind of fixing. They're thinking about the stuff that fixes. They don't really interact. They behave separately. Okay, notes. Okay. Where are we going? We're going L over K, M intermediate. Map that sends M to the Galois group of L over M is a bijection. The degree of, what am I writing here? G over M? No. The degree of something is equal to something else. Is equal to the size of that Galois group of L over M. So this is probably L over M, isn't it? The degree of L over M. Double check. It's good for me, it forces me to learn these things. Yeah, L over M down here. And then this last bit, Galois extension if and only if G Gal, that thing is a normal subgroup of L over K. What do I want right here? M over K. M over K. So I want the colon notation in here. L over M. L over M. So M over K is Galois extension if and only if Gal LM normal subgroup of Gal LK. Good stuff. Okay. What's going on in here then? Have I written that down correctly? So G subscript M is the notation in this section for Galois group of L over M. It should be a normal subgroup of Gal of G over L over K. Normal subgroup of L over K. G L over that's Gal GM. GM is L over M Galois group. GM is, yep, the Galois group of L over M. Good, okay. Learning. That proof looks quite short. Let's have a quick look. It proves that this thing and this thing. First proof that's consequence of that's a Galois extension, fine. And that's the Artin's lemma thing. All that stuff about up and down. The equation is a consequence of 3.17 ages ago. Oh yeah, the sort of counting thing. Consequence of the Tower law and the fact that I love the Tower law is okay. Okay. Yeah, good. 3. M is an intermediate field, M over K is Galois. Then for all gamma in that one, gamma of M is M. Consequence of 3.13 III. Which obviously I can't remember, so we're on page 24 at the moment. I'm going back to 3.13 III just to look at what it was. The images of all maps of K extensions. Oh, okay. Oh gosh. The image of maps of all K extensions. Oh, is there something about playing with the splitting, etc. J over K be any K extensions, any images of all maps of K extensions coincide. Gosh, really? Doesn't feel relevant. Page 24. In particular, there's a homomorphism that goes from there to there, given by the formula. Just restrict. The kernel of this homomorphism is GM by definition. Hence GM is normal in LM by the first isomorphism theorem. This is lovely. This is really good. I really like this. There's a homomorphism from between, those are groups. So there's a group homomorphism. And the kernel of that group homomorphism is that, so that's normal by the first isomorphism theorem for groups. So any attempt to explain this is going to have to use isomorphism theorem for rings and the isomorphism theorem for groups, which are pretty similar, but still, hey, knowing both. Right, okay. Other way round. Suppose now that GM is a normal subgroup, let gamma be in that Galois group over there. We compute from the definitions. Oh, here we go. G subscript. Okay, so this is gamma of M. Big calculation. Fine, okay. I'll skip it for now. By I, we conclude that gamma of M is equal to M. Okay. Gamma of M is equal to M because the first part said something about that being a bijection. Again, we have a homomorphism into the automorphisms of K over M, but that's what the Galois thing is, right? From 2 in the first isomorphism, then we conclude the image has cardinality of K. On the other hand, by Arthur's lemma theorem 3.1 and 3.17, we've got to memorise those really. They've got to be really familiar. We know that that is a number, so that is that. Oh my goodness. Place this. Tower law one more time. Particularly M over K as a Galois extension of the map is subjective. The map of M is obtained directly from the map of M in the first isomorphism theorem. Oh my goodness. Established in the course of 3 above, and it's also a consequence of it. Let's read this note. The notes are going to be good. Established in the course of 3 above, and also a consequence of it. Let I be the map that sends K into L be a Galois extension from K to L. Let M be a subset of L, be an intermediate field. Then M over K is a Galois extension if and only if all the maps of K extensions M to L have the same image, which must be M. All the maps of K extensions M to L have the same image M. Suppose that all the maps have M as an image, then for all gamma in there, gamma represent M, and so M over K is Galois extension. On the other hand, if it's a Galois extension, then we must have gamma of M as M by 3.313 and 3.183. No. So final corollary here. Let that be a finite separable extension. Then there are only finitely many intermediate fields between L and I of K. This is going to be because you make a chain of normal subgroups or something, and it's finite degree overall. The products multiply up. Without the strategy, replace L by one of its extensions. Why would you extend L? Okay. Existence of splitting fields, we must thus suppose that the extension L over K is a Galois extension. In that case, oh, we could extend it to make it into a Galois extension. Extend it further. In that case, the statement is a consequence of theorem 4.4 and the fact that Gal over L is finite and thus has finitely many subgroups. Excellent stuff. Okay, some lemmas. Could have been proved right after 3.18, ages ago. 3.18 was the thing with the kind of triple equivalence that set up the things we're going to need for Galois groups. Lemma 4.6, L over K be a finite Galois extension. Alpha be an L. Then the minimal polynomial of alpha over K is the polynomial. Here are your roots, I suppose. Finite Galois extensions are separable and normal. Separable means that minimal polynomial separates, and normal means. Oh gosh, I do need my notes one more time. Sorry. Still learning. I'll let you know when the learning is finished. Algebraic field extension is separable if the minimal polynomial is always separable. It's normal if the minimal polynomial always splits in L. Handwriting is some of my worst. Okay, so skimming back down here. The minimal polynomial over K really is this polynomial. So I'm going to imagine C over R again. Imagine alpha be some number in L, 1 plus I or something. The minimal polynomial of alpha over K is the polynomial. Multiply together, please, x minus beta, where beta is in the orbit of the Galois group of L over K, flippity flips. Oh, multiply it by x minus beta and x minus complex conjugate. That's the minimal polynomial, comma alpha. Oh, the orbit of, yeah, the orbit of the Galois groups, that includes alpha, x minus alpha, alpha's in L. That's not a polynomial of a K, is it? The orbit of Galois group of L of K moving around alpha. That's an L. Maybe it works out. Already seen part of the argument in 3.18. Okay, fine. Let that be the minimal polynomial. So at the beginning of that proof. Oh, I've got to learn 3.18 really well. That P of x is in Kx. That's surprising. Then by the definition of the minimal polynomial, we have that divides P of x. And we're going to check it's irreducible. This looks very difficult. Hi Diggs, how's it going? We are learning Galois theory, and it's getting good. It's getting good. I feel like we're getting close to some sort of structure theorem sort of thing that's going to tell us about. Well, we've got something about normal subgroups now, and the Quintic that we're looking for, it corresponds to a Galois group that doesn't have very good subgroups. So we're going to be able to write that as a very interesting chain. Yeah, cool. Right, okay, I'm going to skip most of this proof, I think, and come back. Set of roots contains a subset. No, I've been distracted by it again. Just stable under that and has cardinality strictly smaller than its degree. Oh, I saw it 3.8, this polynomial, but I didn't say at all at 3.18. God, I learned 3.18. Let's put a kind of note to self somewhere. I don't know where to put this. Not in my maths notes here, but in kind of maybe some sort of like learning notes. Sexual growth rate, really important. And the proof is really important. Notes. Proof is really important. Okay. So down here, we need the following group theoretic terminology in the following lemma. Good. Okay. Give it to me. Let's go. Let K be a field, and let no. I scroll too far. No, here we are. A finite subgroup G of S of n. Oh, we're talking about subgroups of S of n. It's called transitive if it only has only one orbit. Everything can go everywhere under this. Within my subgroup, I can move anything everywhere. So my subgroup's not just shuffling separate bits of cards. Any card could go anywhere. You're going to shuffle some cards. A transitive set of shuffles to let you, in some combination of those shuffles, move any card anywhere. So if your shuffle is just shuffle the top half and shuffle the bottom half separately, there are loads of shuffles in there, loads of things you can do, but that subgroup isn't transitive because not every card could go to every place. Card tricks. Suppose the P of x has no repeated roots. Let phi be mapped from the orthomorphism groups of L over K. That's L preserving the K structure. Think of L as a field extension of K to S of n with a map such that, here we go, gamma of alpha I is the image of alpha I onto that map, gamma, whatever. What's gamma? Oh, for all I. No, what? For gamma? Oh no, this is defining gamma? Yeah, it's taking. Phi takes from gamma. So phi goes from something like gamma in that automorphism set, which is a group, to something like. Is it alpha I? The things that live inside. No, so SN is the permutations. Okay. Phi of gamma is supposed to be a permutation of I. Okay, so the automorphism. So start with an automorphism, and then where does your automorphism take alpha I? Your automorphism takes alpha I to alpha 1 goes to like alpha 3 maybe, and then that says that phi of that shuffle, so it's like your automorphism gamma takes that. So phi of gamma is supposed to be the thing that takes. Phi of gamma is a function in Sn that takes 1 to 3. Oh my goodness, we've got such chains of functions. We've got right here, look, in a subscript down here, let's zoom. In a subscript over here, I never zoomed in that much. Oh no, change the page. In a subscript over here, we've got, this is what we're trying to understand, a map such that alpha, can I point? I can still point. Alpha I over here is being sent by gamma, which is a map in the automorphism map. That's being sent to some other alpha. Which alpha is it being sent to? Well, complicated. That's one of them, isn't it? Because alpha I is going to something, and then which I is it? So if alpha 1's going to alpha 3, I'd like phi to be a way of keeping track. It depends on gamma, and takes numbers like 1 and gives me numbers like 3. So if gamma takes alpha 1 to alpha 3, I would like phi of gamma, depends on gamma, to take 1 to 3. That's really hard to pass. Let's zoom back out. Okay. Here's the lemma. Phi is an injective group homomorphism. Fine, okay. If P is irreducible over K and has no repeated roots, then the image of phi is a transitive subgroup of Sn. So important to understand this. Oh, and here's the discriminant or determinant, whatever it was called. The element that capital triangle. That's right, we got capital shapes now. It's capital delta. The element big triangle subscript P, which is something to do with those roots, the kind of product of the squares of differences, lies in K. It depends only on P of X. Oh, it's independent of the. Depends only on P of X. Rather than what, right? Rather than the roots. Well, P of X really depends on the roots. Suppose the characteristics not 2. Fine. I'm only going to be thinking about characteristic 0, to be honest. Suppose that P of X has no repeated roots, then the image of phi lies inside AN, in Sn, if and only if that thing is in a set of non-zero squares in the K. I'm writing out something that's just here, right? A set of non-zero squares. There's that polynomial. Yeah, here it is. Product of the squares of the differences. You can each thing once. That's in ZX. How could that polynomial possibly lie in K? It's in Z. Oh no, but you've plugged in alphas so that it will be in K, because the alphas lie in L. I'm surprised it lies in K. I'm surprised that this thing, where is it? Oh yeah, okay, so 3 lies in K, exclamation mark. and depends only on P of x. Was this a little bit like discriminant of a polynomial? No. This thing good. Okay. So this thing calculating depends only on P of x. Oh, what could that mean? What could that mean? We'll have a quick look at the proof just to see if we can get more information about what's going on. That was, okay, 3. Note that. There's the polynomial. On the other hand, 2.16. That's a unique polynomial in K, such that, oh gosh, right, okay, you could write the discriminant in terms of these symmetric things. Oh no, yeah, okay. It's symmetric. Hence, that this object, when you plug in the alphas, is something to do with the coefficients. Oh, these sigmas, we had them before. That's what the sigmas are. I was confused by them before. They're the symmetric things. They are related to the coefficients of a polynomial, Vita's law and stuff. Okay. There's a unique polynomial Q that expresses exactly what that is. And that's Q with coefficients in K. Now, how are you going to get to this polynomial being in? Oh, right, hang on. So when you plug in the alphas, Q of these s's is exactly this discriminant. What are all these minus signs for? Q of minus 1, A0. So all these minus signs from the kind of Vierta's law thing about the relationship between the coefficients and the roots. Very exciting. We're getting back to A-level maths. This thing at the end here says that the constant coefficient in a polynomial is pretty much the product of the roots up to minus signs. That's what this minus sign is doing. So a unique polynomial Q in K of x such that Q of the symmetric object things is equal to that discriminant or determinant or whatever we're calling it. So when you put the alphas in, I want to go back and learn those sigma, that thing about sigmas and symmetric operators. I sort of wonder whether these sigmas are supposed to be the same thing as the s's. Can't remember the difference. So when you go back and do it, this delta, when you put in the alphas, is Q of the s's. Why is that now? It's just reading off the coefficients. And that depends only on P of x and lies in K, so we're done. Okay, fine. Why have we gone back and just looked at the coefficients? What are we doing? Alpha 1, alpha 2, Q. Oh goodness me, this is the relationship between the s's and the x's from before, maybe. So these s's. Wait, yeah. Hang on. So these are supposed to be the symmetric sums, I think. Symmetric sums. I don't know what these s's are anymore. Okay, come back to it. Compute this. Oh my goodness. So ages ago, this morning, I had a bit of a trudge through learning what this triangle was, and it didn't turn up for 20 pages or something. And now here it is, being useful. So that's good. We got a use out of this thing. For any gamma in the morphism group we have, and this thing is going to do some permutation stuff, right? It's going to permute those. I'm just going to give you the sign of permutation. Ooh, so that element delta-y thing is in K if and only if the image of phi lies in AN. I know that delta is in K if and only if that thing is in. squares of non-zero elements. Now, it's just a note that, so it's going to be hard to understand. Trivial fact that this thing is 0 if it's got repeated roots. Okay, so it's unhelpful. Okay. On the example sheet, apparently kids prove that that is true. As a way of expressing, so this is an expression for x1 minus x2 squared, x2 minus x3 squared, x1 minus x3 squared, in terms of S1, which is supposed to be the sum, and S2, which is the sum of products, and S3, which is the product of all of them. Apparently this is true. Symmetric functions in 3 variables. I don't know what those sigmas were doing. I'll come back to it. Now let P be that cubic in Q of X. Oh my goodness, here we go. Polynomial P has no roots in Q, and is thus irreducible over Q, particularly has no multiple roots, since the characteristic of Q is 0. See after lemma 3.6. That's exciting. Never seen that before. There's a fact about Q to mean this polynomial's got no repeated roots. Oh, it is an irreducible kind of thing. Right, good. L over Q be a splitting field for P, field over which it splits. Fine. And then you get some roots. We have S3 of that is minus 1/3. Oh, reading off the coefficients. Thus, it's in Q star squared. Okay, another proof that P has no repeated roots. Conclude from 4.7 that Galois L over Q can be realised as a subgroup of A3. This is very exciting. A subgroup of A3 because it's 1, not minus 1. No, it's in the squares, so it's a subgroup of A3. So this leads directly onto the subgroup of A3 onto here. We know that at least order 3 because the extension alpha I over Q has degree 3 for any alpha I. In fact, the extension has degree 3 followed from proposition 3.9, and from the fact that P of X is irreducible, and this has the minimal polynomial of alpha I, degree 3. The fact that L over Q has at least order 3 now follows from the Tower law and theorem 3.7. But since the size of A3 is only 3, we conclude that Galois Q is A3. So the Galois group of the extension of the solutions of this cubic, which we haven't solved, but the solutions of this cubic have this kind of Galois group A3. Not the solutions, but the field formed by their solutions, which I'm drawing like this because it's kind of triangle. Okay. Right, we're an hour and a half on this afternoon. How are we doing? Do you want to push on? So we've got the theorem of the primitive element. I kind of want to do some notes on what we just saw. This, all of this. Fundamental theorem, I think I got a note on that in my notes. But there's a more, something in here about minimal polynomials. And there's a massive thing in here about splitting extensions. Okay, so I'm going to get some notes in there about what's going on here, and then we can move on and look at theorem of the primitive element. And we're looking at doing some calculations now. There's some numbers turning up, which is getting good. Okay, this is going to be page 27. Quick foreshadowing look. This is going to be the end of section 4 over here. I will have a quick look at this then to finish up section 4 before we do those special classes, the kind of mountains near the Quintic. Let's look down here. Theorem of the primitive element. Be a finite separable extension of fields, then there's an element such that L is O. It's a simple. Oh, if it's a finite separable extension of fields, then it's a simple extension. Suppose the case an infinite field. Okay, fine. Case of finite field is in the exercises or something. since L is a finite extension of K, L is generated by a finite number of elements. By inductional number of generators, you can just get it down from 2 to 1 or something, 3 to 2 or something. So suppose that L is generated as a finite extension with beta and gamma. They're all simple. Does this always happen? Sufficient to prove that L is generated by one element if it's generated by two elements. So, okay, for D and K, consider the intermediate field beta plus D gamma. There are only finitely many intermediate fields. Since K is infinite, thus find D1 and D2 such that they're not equal, and that okay, K is infinite, and there are only finitely intermediate fields. So just find two elements that do this. There's thus a polynomial. Oh, this is great. There is just thus a polynomial such that what was K doing there? K of no, lost it. Such the extension is the same. Those fields are the same. There's a polynomial such that P of beta plus D2 gamma is beta of D1 gamma. Thus we have, and then gosh, gamma is blah, and beta is blah, and in particular, it just works. Oh, this is how you might construct. So let's think about, we saw ages ago something generated, an example of a simple extension. We saw Q generated by root 2 and I. Is that what's going on here? Then there is an element that does this. So sort of like a polynomial. Yeah, okay. Okay, maybe that's what's going on here. Find, so what was that polynomial doing? D1 not equal to D2, and then just go for it. Oh, it's amazing. What is this, some sort of like linear thing? Good, okay. So that's going to be section 4. I'm going to take a 5-minute break here. I don't have the ability to play an ad, and I don't really want to. You are welcome to go and watch an ad if you like. I don't know where you're going to find one, but if you want to go and I don't know, search YouTube or something and find some adverts for products, you can do. I don't get any money for it. Don't worry, I'm not going to get any money off you. But if you want to watch some adverts, then you can do that. If you want to, take a study break, 5 minutes. We're going to meet back here to write up some notes on what we just saw, and then move on to section 5, which we're really getting somewhere with this. Good, right, okay. See you back in 5 minutes. Back soon. Hey! Right, okay. Whew. Oh, I've gained viewers. I always wondered if that would happen. If you've joined in just to look at the back soon sign, then sorry, but we're talking maths again. And it's getting good. We've got some Galois theory now. Let's take some notes on the Galois theory that we were doing before break. We had this really good lemma over here that we were trying to understand. P of x in K of x. There's a lot here. It's 4 statements. How much of this do I want in my notes? Took a break, made another hot drink. Having a go. L over K be a splitting extension of P of x. Those be the roots of Px with multiplicities. Oh, gosh. But then suppose it has no repeated roots. Suppose it has no repeated roots. This thing. Okay. So L over K is splitting extension of P of x in K of x. That's got to be the start. So note L over K splitting extension. Come on. Extension of P of x in K of x. With roots alpha 1, alpha 2, alpha n. Okay, that's the setup. You've got a splitting extension over splitting extension of P of x, and those are the roots with multiplicities, but I'm going to assume no repeated roots really. We've got that map, this complicated map, which is an injective group homomorphism, so fine, okay. That's an element. L is generated by the roots because this is the splitting field. No repeated roots has got to be in there. And then I need to write down this thing, going from the automorphisms. Okay, wait, is that the Galois group? Is that just the Galois group? Automorphisms, okay, how am I being daft? I think that is just the Galois group, and we should not miss the opportunity to write down Galois, right? Yeah, automorphisms with L professing the K structure is Galois group over K, right, okay. And I'm going to write no repeated groups. Then. And there's several things that follow. One of them is that this map phi from the Galois group to Sn such that show me something from the Galois group that permutes elements, permutes the roots. Oh, that's the phrase we're using. That's the phrase we're using. The Galois group permutes the roots. Okay. Then, this is a very slow process of me turning some very well-written notes into some really terrible written notes with terrible handwriting and layout. What are we doing? Then, phi, which maps from the Galois group of L over K to, where's it going? Yep, no, lost. Going from automorphisms to the symmetric group by, what do we want? We want phi of gamma defined so that the way that gamma takes alpha I is that it takes alpha 2 phi of gamma of I with 5 gamma. This is it. So 5 gamma reminds me that if I take something gamma from the Galois group, GGG, into Sn, like this, and then that Sn, this Sn over here is going to act on the I. Okay, what are we saying about that? Is a group homomorphism. Is it isomorphism or homomorphism? Kind of only impressive if it's an isomorphism, right? It's an injective homomorphism. Injective group homomorphism. Injective group homomorphism. I think the best thing I can do today is just rewrite things using my own words. To take complicated things and just to rewrite them. So I'm going to keep flipping back between the complicated thing and my notes. Things feel really scary when you see them in the lecture notes, and then trying to rewrite them in your own words forces you to actually understand a little bit what they're saying. Right, if p of x is irreducible over k and has no repeated roots, then the image of phi is a transitive subgroup of Sn. Ah, boy. So p of x is irreducible over k, so it gets all of its roots from the splitting extension. Yeah, okay. Okay. If p gets all of its roots from the splitting extension, but what we're going to write is if px irreducible, then, so this is the bit where then it gives a transitive. The image is transitive? No, back in again. See, look, I have to remember it just for a few seconds, but I have to remember it. P is irreducible, no repeated roots. Okay, so I forgot the no repeated roots bits. Then the image of phi, no, I'm up here. The image of phi is a transitive subgroup of Sn. Okay. Memory game, right? Irreducible, oh, I had no repeated roots. Then the image of phi is a transitive subgroup of Sn. Anything could go anywhere. Okay. Anything could go anywhere. Maybe why we're interested in irreducible polynomials, right? So then we've got this capital delta thing. Delta of the roots lies in k and depends only on p of x. I don't really understand what depends only on p of x could possibly mean, but fine. I'm just going to write down, for now, I'm going to write down the delta of the roots lies in k. Okay, a bit more. One last thing. This thing about sign of the permutation. So sign of the permutation in here down the bottom. The image, oh hello. Suppose that if the characteristic of k is not 2, which it really shouldn't be, and p has no repeated roots, which I've put at the top. This sort of special case in 3 where if p does have repeated roots, then I think it's just 0, which does lie in k, so whatever. I suppose depends only on p of x kind of means you've got enough information in p of x to deduce it. Fair enough as an observation, I suppose. Okay, so I'm going to go and put in if characteristic k is not 2, then the image of phi is in an if and only if. And there's a technical thing there. And why are we writing this? Oh, this is okay. If the characteristic of k is not 2, then image of phi lies in is in an if and only if that delta thing is non-zero square in k. Non-zero square in k. Let's have a look at those non-zero squares again. K star squared. It's the set of non-zero squares in k. Non-zero squares. like most things are squares, right? Oh, it's like being positive, right? It's like being positive discriminant. Is it called the discriminant? The set of non-zero squares is like positive numbers in the reals. I think that's what it is. I think it's discriminant. I think it's been discriminant all along. Oh, here we go. Got to find it again now. We have in here somewhere near the front this definition of what these things are. Oh yeah, here we go. It's down here. Symmetric polynomial, and we had some examples of them over here. This thing was called the discriminant. Brilliant. Okay, so it tells you whether you lie in AN or SN. Non-zero square in K. So way up here, where I had this definition of capital delta, I want to remind myself that that is discriminant. Like, oh no, what do we call it for a quadratic? The discriminant of a quadratic, right? If we're getting my words right. Yeah, the b squared minus 4ac thing. The thing that Reminis Fifth is calculating quite a lot. It doesn't look anything like the discriminant of quadratic though. I guess it's maybe discriminating something else for me, but I might go and calculate it for quadratic at some point. What do I need to calculate for a quadratic though? Oh, something with two roots. Something with two roots. So you'd have to do something like, if you had two roots, it would be like alpha 1, alpha 2, which would be just alpha 2 minus alpha 1 squared. And that, I happen to know, if your polynomial's got real roots, that'll be positive, and if it's got imaginary roots, that'll be negative, because the difference will be a multiple of I. I think this is good. It's not b squared minus 4ac though, is it? What's b squared minus 4ac? That's something like distance as well. Wait, so this is b squared minus 4ac, right? Let's try and work out how, in what sense is it b squared minus 4ac? So let's try and write it out in terms of the symmetric things. The coefficients are more like symmetric functions than they are like anything else. So this is alpha 2 squared minus 2 alpha 1 alpha 2 plus alpha 1 squared. I don't know why I've written it out that way. Never mind. Which is alpha 1 plus alpha 2 squared. Take away 4 times alpha 1 alpha 2. There's the 4. Which is, in terms of the coefficients of x squared plus bx plus c or something, b squared minus 4c. There's your discriminant. That's the link. So we've got a way to move discriminant to higher degree polynomials. Like it's like divided by a squared or something, like for a monic polynomial. There's secretly like divided by a squared or something. What is this really? If I have an a in here, then it's this divided by a squared, and this over a, so it's distance up to a factor of a or something. I'm worried about positive and negative numbers now. That's b squared minus 4ac. The discriminant we know and love divided by a squared. So maybe yeah, maybe that means that really the quadratic formula should look more like this, right? I could even do something with the twos and 4s probably. But if you move the a squared inside, then you get something in here which is really like the discriminant in terms of this Galois theory definition. Ooh, we are building understanding. No one can stop us. No one can stop me. I've worked out a way that things like the discriminant that I know and love. Okay. In terms of the coefficients of a polynomial, it's not that bad. Back up a little bit. Where are we at? Excuse me. So this tells you whether it could be an AN or SN. Characteristics not 2. So I'm thinking about real polynomials, real quadratics with no repeated roots. There's not more than I can chew there, because the problem with only dealing with C over R is that it's got dimension 2, which means that the subgroup structure is really, really boring. It's so small, the complex numbers, so tiny over the reals. I need some better imagination, right, to put in like root 2 and I, and then you get something slightly non-trivial as the roots of some pretty straightforward equation. Right, good, okay. Getting a little bit closer to understanding why there's so much polynomial down here at the bottom and so much stuff going on with the coefficients. Okay, good. And then we found this one for 3. Oh, great, something to calculate. And then go and calculate this. Oh my goodness, look at all that. 27, S3. Oh, crikey. Are any of these 0? Oh yeah, S1 is 0, so this is going to eliminate most of these terms except this 4, minus 4, that one cubed, minus 27, that one squared. Good stuff. We're looking for a monic. Is it a monic polynomial only? Am I comment about A good or not? Not sure. Okay. This is a subgroup of A3. So that means something like, it's not just like having real and imaginary roots, but it's a bit like, I guess if you have real roots, then no, okay. I was going to say something silly about extensions of dimension, but not quite. If you have real roots, they're just 2 real numbers. Oh gosh, they're both. There's something you can do with this, isn't there? A sum. If you've got rational coefficients, then your 2 roots sum to a rational number. So if you extend Q by just throwing in one of the roots, you're good. But that would also have dimension 2, right? A2. A2 is just the identity. Anyway, I should stop thinking about quadratics. Then, theorem of the primitive elements. So, theorem of the primitive element. L over K, a finite separable extension of fields. Here we go. L over K, a finite separable extension. Okay, finite separable extension. That's pretty general. Of fields. Then there's an element alpha in L such that L is a simple extension. Exists alpha in L such that L is the extension of K by throwing in just alpha. Really? Really? L is the extension of K with just alpha. Amazing stuff. Good. Okay, and calculation here to how to make it simpler. Which I think if I follow through with root 2 and I, then things over there will simplify down. So this means that simple, they can't have very good degree. Oh, it could be a really high polynomial. If it's algebraic, it might have a massive degree, so it's not particularly telling me that it's quite straightforward. Is it telling me there's nothing in between? I'm not sure. It's finitely intermediate fields. Oh, good. Right. Okay. Right. Let's look at special classes of extensions. Let's quickly look at the map. Just kind of overview of how this is going so far. Yesterday, we travelled long and far through ring theory. We found out about rings of polynomials. And we learned about what a field extension was for the first time. We learned about finding a root by throwing in some extra stuff. Today we did a bit of trudging through Galois theory, but then things started looking up when we started to see that some of this was literally the Galois group that we needed, and that some of those things were what we're going to need for like the way that subgroup structure relates to the field extensions. We're getting quite near the Quintic on our quest, at least for a first pass through of just skimming the notes to find out what's there. I want to go and look now at the next bit of the notes, which is called section 5. And it's got these 3 kind of sorts of extensions that I think these ones are explicitly relevant to the problem of solving quintics or whatever with radicals. So I've drawn them in the map as kind of foothills of what we'll experience on the way up to the Quintic. I'm excited because it's probably only a couple of hours away before we, for the first time, get to the Quintic and maybe have a chance of getting like one hand on to understand what's going on. That's the understanding journey that we're on. Okay, cyclotomic extensions. Okay, so we've got 3 sorts of extensions to understand. Oh, I've lost them. There they are. For any field E, define mu n of E to be the set of rows in E such that row to the n is 1. The roots of unity. There they are. The roots of unity in E. Nth roots of unity in E. I really love the phrase roots of unity. I've heard it before for complex numbers. I suppose, yeah, sure, you can do it for any field E. I've never called a field E before. E. That's a finite cyclic group. Huh. It's an exercise. I kind of feel up for that. How hard can it be? So it's a field, so it's going to be really nice. Finite. Interesting. But the field could be massive, right? The set inherits a group structure from E star. Fine, okay. It's cyclic. So finite would be, once you know it's finite, it's something like, for complex numbers I say people want a small argument, but that's nonsense here. From E star, E with multiplication. E under multiplication, I suppose. Why is it finite? Oh gosh. At most one subgroup in G, which is cardinality mod G. A finite commutative group. That's like, that makes it sound like we know it's finite. Why would that be finite? Can't I just take a really huge field where there's loads and loads of stuff that raised to the power of n gives me the identity? It's some infinite dimensional field. Like loads and loads of copies of how do you make a big field anyway? Extensions. Are there only n of them? Oh, if the number is n. Wait, what? At most one subgroup in G, which I can't actually group G. That would mean that's finitely generated. It means it's cyclic. I'm struggling a bit with why this is finite because sure it says for any field, right? Well, I don't know anything about any field. Okay, so suppose there's loads of them. I guess there could be fewer than n. There can't be more than n. Is this going to be the punchline, right? There's at most n of them because they are the roots to... Yeah, they're the roots to the equation x to the n equals 1. Roots of x to the n equals 1, which really feels like it can't have more than n solutions. I should be able to prove that really. Let's think. If it had lots of roots, I would probably write them all down and multiply together. X minus x1, x minus x2. I'd get a polynomial with higher degree. And then I'd have two polynomials where, yeah, on the one hand, I'd have this polynomial, which has all of these many roots, and I'd have the large polynomial that comes from multiplying out literally all of this. And maybe I could look at those two polynomials and say, what's the ideal generated by those polynomials? What's the minimal polynomial? Or something. No. Wait, yeah, just pull out the factors. Pull out the factors one at a time. Use that kind of factor theorem thing, right? Just pull them out. Times, yeah, you can factorize it for me. Pull out the factors. Okay, yeah, one at a time. At most n. Good, okay. N through its unity. I think there's at most n. Okay, if there's exactly n of them, which are called omega, primitive n3. So generate. Oh, fine. I haven't shown that it's. Cyclic. It's a generator of all of them. Right, cool. Because n could be like the 8th root unity in the complex plane. Not all of them are generators. If this terminology is not used, oh gosh, okay. If there's not n of them. Note that if that is a primitive nth root of unity, then all the other primitive roots of unity form that to the k, where k is an integer prime to the number of them, prime to n. Okay. We would also need the lemma 5.2. Finite cyclic group. Let k be the size of group. Let I be, oh gosh, the map given by the formula. Ah, look at this formula. I from the units of zk. Oh, is that zk with multiplication? I think it might be zk with multiplication. To automorphism of groups G be the map given by the formula I of a mod k of gamma. It's gamma to the a. Right, okay, up to k. K is the size of G. It's an isomorphism like Lagrange or something. Fine, okay. So that big I is going to map things over there. Now let k be a field, and suppose that I guess highest common factor of n and characteristic k is 1. So not 0. Okay, we'll move on. Let L be a splitting field for the polynomial. Using language, which will sometimes in the following denote such a splitting field by k of mu n. L is only well defined up to isomorphism again. I've done a couple of times. Note that xn minus 1 has no repeated roots, because that is 0. Ooh, that was the definition of repeated roots things. Back over there, ages ago. So the number of roots there in the splitting field is n. It's a Galois extension because it's the splitting field of polynomial separable. In particular, since mu n of L is like it's isomorphic to z mod nz by 5.1. Yep. See that there are that many phi of n primitive nth roots of unity in L, the splitting field, and the most you can have. Okay. Ah, good. There are at most n. I put star after, I think, but now I'm pretty much certain. Good. Okay. In particular, yeah. Here, phi is Euler's totient function. There are a number of things there, co-prime to n. Good. Okay. Good old Euler. Turning up just at the right moment. Proof is an exercise. Wait. What did I do? Oh, I zoomed. Zoomed the wrong way. Okay. Cool, good. So in the splitting field, you get as many of these as you're ever going to get, right? No, wait. In the splitting field, you get not necessarily n of them. No, you do get n of them. In the splitting field, you get n of them. And not all of them are primitive. The ones that they have to be co-primed to give you primitive ones. So in the splitting field, you get n. So that's the polynomial, and if you actually split it, so that you get n roots. Yeah, okay. In the splitting field, you get n of them, not all primitive. Good, okay. Right, what's this? What on earth is that? It looks a bit like the tuition function. What are we going to do? Subscript n and k, b, the product over the primitive ones. In k, what was k? What's the relationship between k and e? Is k the... Maybe they're supposed to be the same thing. I can't see any e's anymore. Oh well. Yeah, it's got to be the same thing, hasn't it? It's got to be meant to be a k. Note that the degree of that polynomial is the number of them, sure. Also note that L over k is a simple extension. Because L is finite or something. Oh, you can just generate it. Here's what you're going to generate it with. Any primitive nth roots, because that will then generate all of them. Okay, L over k is a simple extension. Right, these are the nth roots, by the way. For people keeping score of where we are with the Quintic, this is the idea of nth roots. We're getting there. Coefficients k depends only on n and k. This is a symmetric function thing, right? Yeah, the coefficients are symmetric functions in the primitive nth roots. Since the primitive nth roots are permuted by the Galois group, the coefficients are thus invariant and lie in k. Gosh, there's a lot going on there. Polynomial only depends on n and k because all the splitting k extensions for x to the n minus 1 are isomorphic by 3.13. 3.13 is also going on the very important list. Let's find the very important list. This is kind of notes to self on the way through to next time through. Make sure that I pay lots of attention to particular sections. Okay, polynomial in there has coefficients in k and depends only on n and k. Keep saying it depends only on n and k and not x. I mean, it's a polynomial that definitely have x. Anyway, right, there's a natural injection of groups from the Galois group to automorphism of these things as automorphism as groups of the, because that's what they are, the nth roots of unity of L. The map is surjective if and only if that polynomial was irreducible over K. How are you going to access? Okay, surjective would mean it hits everything. Ooh. Canonical injection of groups from 5.2. Right. So, what do we have? Mu and L generates L. Gosh. This is for a particular L, isn't it? This is not just any L, right? Or do the mu and L always generate L? I think this must be in the context, right? Yeah, well, L over K. Galois group of L over K acts on L by ring automorphisms. It is the group of automorphisms of L that preserve the K structure. Omega be a primitive nth root of unity. Suppose that polynomial is irreducible over K, since this polynomial annihilates omega, it must be the minimal polynomial of omega. Why is it minimal? That's irreducible. Yep. Hence, this thing is the degree is bigger than or equal to 5n. Thinking about the degrees of the polynomial and the degree of the field extension. And thus we have the size of the Galois group bigger than or equal to 5n. That's pretty cool. On the other hand, the size of the Galois group is less than or equal to 5n by part 1. Oh gosh, because the Galois group is injected into that automorphism of groups, and the size of the automorphism of groups. To do an automorphism on the groups, you've got to send the generator to a different generator, and there's only 5n of them. Hence, the Galois k is 5n. They conclude from I that little phi is surjective. So a map is surjective if and only if that's irreducible. Where do we use the irreducibility? Somewhere in the middle about it being a minimal polynomial. Right. Okay, so irreducible in there tells us it's the minimal polynomial. Right, okay, I'm mumbling quite a bit, really trying to make progress now. Here's a special one. Down here, polynomial 5n. I do not enjoy this. NQ of x is irreducible and has coefficients in Z. Oh, I do not enjoy that. Coefficients in Z. So n. Then the second thing is Q, because we're looking at the coefficients where I'm pretty sure that's going to be a K. Pretty sure there's a K down there. So this is the roots of unity over Q. Aren't very many roots of unity of Q. Oh, hey, Laurud. Yeah, we're getting ready to find the qubit. Quintic, we've done quite well with Galois theory today. We're skimming through the first time. Doing all right. We've got down to this weird polynomial that I'm trying to understand right now. It's to do with multiplying roots of unity. I really want to get good at roots of unity here because they correspond to nth roots and they're part of the Quintic statement that I'd like to understand. Okay. L will be a splitting field, xn minus 1, of that polynomial in Q. Yep, okay. Omega in L. Fieldsley is off to rehearsals. Let omega in L be a primitive nth root of unity. Yep, okay, one of the ones that generates it. So Q in the rational polynomials be the minimal polynomial of omega over Q. Then that divides xn minus 1 because that was a polynomial that gave us the roots. And thus there is a polynomial. Oh yeah, because the roots have to do this. That's what an nth root of unity does. So a polynomial t of x in rational coefficients that divides it. Yeah, polynomial you could multiply off by to get to this. Note that t and q are monic. Ooh, time to look at the content. 1 over c of t and 1 over c of q are both positive integers. The content of these things. Right, because the polynomials are monic, so any primes that divide the other stuff aren't going to be in the content. Maybe they've got 1 over primes in the other terms, so the content is going to be 1 over some prime power stuff. All those orders in the content are going to be negative numbers, so 1 over them is going to be positive integers. There's the content, Gauss content function. On the other hand, we compute that the content of this is 1 because we can see all of the coefficients. So we know that all these things are multiplicative, so CTCQ is 1, and thus those things are both 1. They're both integers? No, they're not fractions. Well, hey, 1 over CTCQ and 1 over CQ are both integers that multiply together to give 1. So they're both 1, so these things are both 1. So Q and T both have coefficients in Z. Content is 1. There's no none of this divided by 3 in each term afterwards. It's like divide by 3, divide by 4. No, because the minimum. Content in Q is a bit different from content in Z, as far as I understood it yesterday. If you have a polynomial like x plus 1/3, and it kind of feels like that, that's got no common factors, but for Q you've got to consider the fact that this has got like 3 to the 0 and this has got 3 to the -1 in it, so the content comes out and returns 3 to the -1 as the content. It takes the minimum power of each prime in your coefficients, which can be negative if you've got something like that going on. Okay, what is that emoji? It's learning. Let's just take that and put it in over here. Smiling face with a tear. Doesn't display on mine. Oh well. Learning emoji as well. I'm learning so many things today. Goodness me. Right, okay. That's the end of the proof, I think. And then in here, P, prime number P, we claim that Q of omega to the P is 0. Q, oh no. No. These things have coefficients and sets to the end. No. Are we still going? We're still going. P prime number claim. Maybe I shouldn't be reading all this proof right now. Contents, monic polynomials. P power function is additive. Oh my goodness. In FP of X. Oh, we do need to use FP of X a little bit. So then loads of stuff. Multiple roots, however. What is that at the bottom? Is that the ideal generated by, right. Things are coprime. So it's 1, okay. Which is what it means to be separable. Anyway. Right, good, loads of stuff going down here. Polynomial proposition, 5nq. Don't get it yet. Irreducible has coefficients in Z. What are we going to do with it, I wonder? Whenever we've seen an irreducible polynomial, we've been using it to sort of generate a field extension. Oh, if you bring it in, do you get... Okay. Contradiction. I must conclude that that is 0. Applying the claim for various polynomials repeatedly, any integer k was covariant to n, all the primitive roots of unity are roots of q of x. So this degree is bigger than root of 5n. But in fact, q of x is a factor of phi n q, which had degree phi n, so it must be the same thing. In particular, it's irreducible and has coefficient in Z. Okay, it's pretty cool. We should take some notes on this. So again, it's kind of skipping proofs, but we're gonna learn along the way, and we're taking notes. So converting lovely lecture notes into my own handwritten nonsense. I don't know why we had field E at all along here, so I'm going to use K in my notes. I'm going to keep it mu subscript n for the nth roots of unity. Let's go into Questlog and let's go over here and put this in notation, I think. So mu n of k is those elements r in k such that r to the n is equal to 1. Nth roots of unity. Okay. Those elements in k. Yeah, so r to the n is 1. Good, okay. And we didn't write it down as a finite cyclic group. Fine, I'll just remember that. It's not, I'm not writing that down. Right, and there's this notation, big phi nk of x is the product over all roots of unity, primitive roots of unity. So let's write down what a primitive root of unity is as a reminder. Primitive, if it's a generator, primitive roots of unity, generate that group. Oop. Where have I gone? There I am. Primitive roots of unity, generate that group. And it's a cyclic group, so it's not too implausible that there could be a generator. In fact, there's quite a few generators of a cyclic group, depending on the order. Group theory, who are the elves? Their metaphor makes sense to me. Right, I want a definition of this big phi, nk. I want you to multiply together x minus omega, those roots. I think you're going to get x to the n minus 1, right? Oh, just the primitive ones. Okay. So for p prime, I think you're going to get x to the n minus 1, but hey, not my business to question it yet. Omega primitive nth root of unity in k x minus omega. Just multiply together the x minus omegas for the primitive nth root of unity in k. There they are. They're in the primitive nth root of unity of, I think, k. I think that's a typo. And the degree is totient function. That's how many there are. Oh, yeah, that's how many primitive ones there are. Okay. And it has coefficients in k, and depends only on n and k. I'm going to just write down that it has coefficients in k on my kind of results page over here. K of x has coefficients in k. And then down here, the next thing in the notes is to say there's a natural injection over here, and that was surjective. Oh gosh. Do I want this? Maybe. Maybe I'm going to write down phi nq is irreducible and has coefficients in z, because that's kind of cool. Irreducible coefficients in z. Okay, that's pretty good. What a good journey. Proof of that looked really complicated. Okay, that's cyclotomic extensions. Somehow. I don't think we extended anything, right? Why did we extend? Maybe we're going to consider extending at some point using these. Again, we've got a little bit of like, can't see what these are for yet. Can't see what these are for. They seem good. Right, 5.2. Camera extensions. Next of the kind of foothills of the mountain that has the Quintic in it. It's getting good. Suppose that x to the n minus 1 splits in k. Sure, fair enough. A and k and m over k be a splitting extension of the polynomial x to the n minus a. Oh, okay, we're solving x to the n minus a now, are we? Note that that's still got derivative like that, so that's things 1, the coprime, so it's a separable polynomial. So m over k is a Galois extension. That's called a Kummer extension with a k. Okay. A and k, m over k, splitting extension for x to the n minus a is the Kummer extension. Okay, good. Getting there. So splitting extension, really got to learn about splitting extensions, haven't I? If I'm going to understand this properly. That is a Galois extension, okay, because it corresponds to a separable polynomial. One of our definitions of a Galois extension. Splitting extension for that polynomial. I should probably write down this as well, where x to the n minus 1 splits in k. Need x to the n minus 1 to split in k. So this is going to give us nth roots of a, right? So if you have nth roots of a, do I want those? Yeah, the rows in L be such that row to the n is a. There's a unique group homomorphism. Ooh. Galois extension of m over k. 2, this doesn't mention L anywhere. Unique group homomorphism for gamma m over k. 2 roots of unity of the nth roots of unity in k, such that gamma of phi of gamma is gamma of rho over rho. Gamma of rho over rho. This thing is 1, and thus we indeed have this thing is in mu and k, sure. Is this just saying just divide them by rho? What is this trying to say? It does not depend on choice of rho. And let rho be something that satisfies that. There's a unique homomorphism of m over k for any intermediate field, I think. Whereas m, like specifically the Galois extension. Here we are, right. K is a field, splits in k. A and k, the m over k is a splitting extension of that polynomial. L was a big thing. What's L? Such that this happens. But wouldn't that be in M? Because that's the splitting extension? What's L? Unique Greek homomorphism from m over k to the nth root of unity over k, such that phi of gamma. Well, let's try and understand phi of gamma. Phi takes gamma, something from the Galois group, and then computes gamma of rho, where he's earning rho 2 under this Galois group, and divides it by rho. Note that if we use rho 1, then we still get 1. And rho over rho 1, so the n is still 1. So we're an nth root of unity mu, such that this is. Yep, okay. Now using the fact that this splits in k, we may compute this stuff. This function does not depend on rho. Now proof that phi is a group homomorphism. Okay, so we should skip this proof, I think. I really don't understand what's going on here at all. What's L? What's L? We might need a second opinion, I think. Can I read it as M? Let rho and M be such that that's one of the nth roots of unity. Now look at your group homomorphism, where are you sending rho 2 in that extension, m over k. So preserving the k structure. Automorphism is of m, where are you sending rho? But actually tell me where you're sending rho, and then divide by rho. And that will give you a solution to x to the n is a. X to the n is 1, sorry. And that indeed will be, so this will indeed be this. To see that that does not depend on rho, note that if rho 1, a different one of n, is a, then this thing is still 1. So it's an nth root of unity. Oh yeah, okay. This is another example of an nth root of unity, excuse me. Such that rho 1 is mu times this. Using the fact that this splits, we may compute this thing. Oh gosh. And that's, why is gamma spat out that rho? a mu. Oh, we've multiplied to order by mu. This might be easier to write out like this, right? Gamma of rho over rho equals mu gamma of rho over mu rho equals, and then what's going on here? Gamma of mu rho exciting over mu rho, which is then the thing happening to phi 1. Gamma of rho 1 over rho 1. We move that mu inside there using the fact that it splits in k. Splits in k, so we already had all of the roots in k. Right? Is mu equal to gamma of mu and then multiplicative rule? Possibly. Now prove that phi is a group homomorphism. Oh gosh, okay, loads of stuff. I think we're doing that fact again on a lambda down there. You can see some lambdas moving around too, right? Oh, using the fact that gamma preserves. It's doing like top and bottom of a fraction sort of stuff. Lambda of rho and rho. Since these equations are equivalent, good. Okay. It's a simple extension generated by any root of x to the n minus a. Following theory is kind of converse to 5.6. I don't know what L is in 5.6. I think it's fine though. Current extension is a simple extension. Okay, bit stuck down here. Proof of the previous lemma also shows this is a simple extension generated by any root of x to the n minus a. Following theorem is kind of converse. Let's have a quick look at this converse. Generated by any element of any element of need that so any element of generated by any element of what's generating this thing? Any root of x to the n minus a, which those lie in, but then it's splitting, right? Root. I'm confused because I thought that if this is a splitting, if that polynomial splits in k, suppose that x to the n minus 1 splits in k, then, oh, maybe x to the n minus a, I haven't been careful enough. X to the n minus 1 might split in k, but x to the n minus a might not split in k, because you haven't picked up those roots. But really all you're picking up is like the... I think what this is doing, my intuition for what this is doing, is that it's saying you have these like roots of unity for the things that cube to 1 or something, and then if you want the cube root of 2, that's fine, you just multiply them by the cube root of 2. Sort of pick one of them and just multiply it up and it's fine. I think. So take any root. Excuse me. Here's a converse to 5.6. Let K be a field and let M be a positive integer with that. Suppose that xn minus 1 splits in K. Suppose that that's a Galois extension and the Galois group is cyclic. Okay. Good. Facts about group structure versus extension structure. Take the generator and let omega be primitive nth root. Now define beta of alpha to be this combination of the primitive nth roots in K. So if this splits in K, then you can do this sum. Then for any a in L, we have, for any alpha in L, we have b of alpha to the n is in K. K was, gosh, over there. If beta of alpha is non-zero, then L is K of beta. What is this? So the splitting field is like this. B of alpha is non-zero, then L is K of beta. Oh, it's generated by that root. It's generated by that root. And if there's an A alpha in L, there is an alpha in L such that beta of alpha is non-zero. Oh, L root, I missed your statement. What did you say? Could L be a field extension of K with M a field extension of L? Do you think L could be some sort of intermediate field? Yeah, maybe. Maybe L is kind of the splitting field? No, because it splits in K. I was still confused by it splitting in K. I sort of think maybe these are in K. A polynomial splits in K, so I sort of think. Show me the things it splits into, right? Polynomial splits if you can write it as a product of linear terms, I think. Have I got completely off the rails? Something for a polynomial to split. Let's go way back up here. We had about 5 or 6 things that all started with S, and we were trying to learn all of them. Polynomial splits if it's the product of some nice roots. So polynomial splits in K, then I think all these roots of unity are just in K. Such that right at the end is A. Ah, no, because once again, sorry, x to the n minus 1 splits in K. Nobody said anything about x to the n minus a splitting in K. Now I'm back to thinking maybe no. Because m, yeah, okay, so m over k is the splitting extension for polynomial x to n over a. So m is the field where we finally get some roots. So that's the point of m. We get some roots of this thing. So now I think it's m. Be one of those roots. The point of going to m was that it splits, and now we can talk about these roots. Then take a unique group homomorphism, the Galois group of m over k to mu n of k. Wait, so this takes it into this is a cyclic group. So this is saying the Galois group is part of that cyclic group, maybe the whole thing. In particular, it's not very exciting, right? Cyclic group. So Galois is going to come along. The Galois group is going to come along and permute your roots of unity, and Galois can only really do that by rotating your roots of unity. Okay, maybe. And then this converse is going to be, suppose that the Galois group is a cyclic group. Now we're going to find generator. Yeah, take 5. Suppose that then this thing's in K, and there is an alpha such that B of alpha is non-zero. Okay. If beta of alpha is non-zero, then L is the field extension of beta, so that L is the splitting field for x to the n minus beta alpha to the n. Is that beta of alpha to the n? How much does that n apply to? Is that beta a polynomial? Yes. Not the extension of beta to alpha, because beta is not a field, beta is a function. I'm sure of these sigmas as well. Sigma being the Galois group, the generator of that Galois group. It was cyclic. So you can do these things mean take a group to apply a certain number of times. Okay. Right. Oh, here's a proposition by Dedekind. Nice. And this is going to be, let's scroll to here. No. Here, for the proof, we should need a general result in character of groups and values in multiplicative groups of fields. Let E be a field, let H be a group, the character of H the character of the group with values in E, values plural, is a group homomorphism. Oh right, okay, multiple values because it's a map. It takes H from the group to field. Right, so looking at the multiplicative group of a field, so E star, values in E star. Okay, characters of groups. A character of H is a group homomorphism from the group to that multiplicative group of the field. Here comes Dedekind. Proposition 5.8. Let chi1 up to chi k be distinct characters of H. Distinct maps from H to the E star. Values in E star. Let the A's begin E in the field. And suppose that combination is 0. Then they're all 0. Amazing. Oh, that's true for all H in H. Induct on the parameter K. What does this mean? We're adding again. So H is a group and E. Yeah, okay, so this is these things live in the field, so you can multiply and add things. Suppose that you could they're kind of linearly they're better than sort of like saying these are linearly independent, right? Can't add them. Distinct characters of H maps into E. Distinct characters of H. I suppose that's 0 for all H in H, the group. So whenever you take your group, these characters are going to map it into the ring, and then I'm going to combine them together and get 0, and that's not possible really. So induction on the parameter K. Clearly holds if K is 1, because 0 is not the multiplicative group, so these chi things characters never map to 0. So if you've just got one thing that's equal to 0, then it must be the coefficient A1 that's 0. Suppose that K is bigger than 2, the proposition holds for a strictly smaller parameter. If all of the II vanish, there's something to prove. At least one of them doesn't. Reorder them so that it's the second one. Okay, now pick alpha in E such that the character of alpha these are distinct, so you can find some alpha such that chi1 and chi2 are different. For any beta in E, we have this stuff. Subtracting one from the other again, since it holds for any B, you include from the inductive hypothesis. This is like rotation dimension again. Okay, can you imagine that? And then proof of theorem 5.7 has got, what have we got? So 5.7 is all this stuff about the field, and all this stuff about how this kind of polynomial beta, which combine together roots of unity with group action on my element. Yeah, the characters and the characteristics do look quite different. Earlier we had a small victory in that discriminant turned out to be the same thing as discriminant, so that was good. Like the one for quadratics turned up again. It took a while to realise it was the same thing though. Up to reordering the indices. Suppose yeah, okay, no, it's this proof. Okay. So 3.7 very quickly, skimming the proof. Deduce from each I, we have this. Ooh. Wait, what on earth is happening in here? So if you plug in beta of alpha, you do sigma to it, and you'll get what's sigma? I feel like I'm losing the plot quite significantly through the last couple of hours. We're on a little mountain peak, and then these new extensions we've discovered are kind of a bit of marshy. Oh, I don't know what these are for. Adding together these combinations of roots. It's kind of like, I think I've seen things like this in the cubic formula, so I think it's going to come together, but not yet. the extension of k over beta. Right, okay. We're skipping the proof. Okay, right, well now I need to make notes. That was my camera extension. Gal Alk is a cyclic group of n, so this is the way you go backwards. If x to the n minus 1 splits in k, then okay, here we go. So notes down here. So many notes. If x to the n minus 1 splits in k. But today is all about doing this kind of first pass to find out what's out there, so that when we come back we can understand it better. Right, x to the n minus 1 splits in k. L over k is a Galois extension, and that Galois is a cyclic group of order n. L over k, Galois extension, and gal of L over k are cyclic. Then, and the thing that you get out of this is that, oh my goodness, there's some combination of roots of unity such that there's some combination of roots of unity and alpha. We can let beta of alpha be, and what is this? The sum of increasing omegas and increasing applications of sigma. So let beta of alpha be increasing omegas and applications of sigma. N-1 sigma n-1 of alpha. Is it this? It's a real sort of memory test, right? I have to look at the notes, try and remember what it is, what it says, and then write it out again. Right. Okay, so we've got this beta, this, I guess, polynomial. That's pretty good. There is an alpha and L's. That's 3 times, but Google has attempted to help me out. It's trying its best, right? What are we doing? Really distracted me. I think I wanted to be distracted. Okay. Beta alpha to the n is in k. Beta of alpha to the power of n is in k. Not nice, but then beta of alpha to the n is in k. Why do I need that? There's some random polynomial to me at the moment. If it's non-zero, then L, okay, well, slightly better. L is the splitting field of beta. If beta is non-zero, then L is the splitting factor of L is the splitting field of k of beta. So, right, so beta alpha in here. Oh, this tells us about L as a structure over K. This is going to tell us how to find the element that forces this to be, okay, like the converse is we want to get back to saying, aha, that cyclic thing corresponds to you being the splitting extension over some pretty simple polynomial. There's the polynomial. And there is an alpha and L such that the thing's non-zero. Oh, this is good, right? And there is an alpha and L such that you can do the previous thing. And this does happen for some alpha. Good, okay. Slight moment of like, I see what they're doing here. The claim here is that this does happen. There is some alpha and L such that the thing's non-zero. And then that's good because then L really is the simple extension of K by throwing in beta. And beta is literally what you're supposed to calculate. It looks like it's come out of nowhere. But here's a polynomial. So this says that this coefficient is in K, which means that this coefficient is in K, and this polynomial is the kind of polynomial which we're going to use to make the splitting field of L over K. It's the Gower extension because it's going to turn out to be the splitting extension for a separable polynomial. Phew, okay. Oh, there's a bunch of stuff down here. And then I'm going to take some quick notes on characters. So I need a definition of characters. E be a field, like H be a group, a character of H with values in E. It's a group homomorphism H to. So I'm going to write this out with K a field, H a group. Come on, G a group. Yeah, old school. K a field, G a group, F a field. F a field, G a group. F a field, G a group, a character of G with values in F. F field, G group. A character of G with values in F is, and then I've forgotten what it is already, so I'm going to look back. A character is, oh no, it's up there. It's a group homomorphism. Character, and I'm going to call it chi or something, is a group homomorphism from H to the multiplicative elements of F. It's a group homomorphism from G to the multiplicative bits of multiplicative group of F. Good, okay. It's a character of G. And this is, right, okay, what are these then? What's the relationship? I can see a sum. Alpha B, no, the A's B and E, those are distinct characters. Like how the sigmas up here are distinct characters, they're distinct maps from alpha. No, they're not. Oh no, sorry, the these sigma things are distinct characters because they're maps from, no. There are some maps and they go to the field. That's where I'm at right now. And that sum looks very similar. Okay, I think this is going to turn out to be relevant to 5.7. I can kind of see a link, but I'm not too clear on what it is. This kind of says distinct characters are linearly independent, but we'll get there. Obviously, we're going to use that Dedekind thing in the proof of 5.7. And then is this going to explain to me what these things, why these things are, defines a character. Any element of this defines a character on L star with values in L star. So yeah, okay, there is an alpha and L star such that, oh okay, why the alpha exists. Such that B alpha is non-zero. But that was telling me, the statement before was telling me there was an alpha. Anyway, let A be beta b to the n. Okay, so it's looking at those elements. Since those are all roots of that, we've shown that it splits in L. That acts faithfully and transitively on the roots. Conclude that x minus a is irreducible, so the degree is n. Conclude from the Tower law. So I've got such a soft spot for the Tower law turning up in things. I don't understand this proof, but I'm not trying to understand proofs today. I'm trying to get to this idea, the ideas. Okay, it's part of the proof, I think. I'm hoping that 5.8 is only relevant if I'm trying to understand the proof of 5.7, and that I can kind of leave it as this kind of character thing that you need for proving this idea about Gower groups. The thing I want to take away from this, I think, is that if you see a cyclic group, you should start thinking about x to the n minus 1. Not sure that's very good, but hey, there's some link between cyclic groups and polynomial x to the n minus 1. Okay, radical extensions, last foothill, and solvable groups. Here we are. I think we had a quick look at this yesterday. Here we are again. And it starts with a definition. Oops. How do I get back? Okay. GB group. Finite filtration is a finite ascending sequence of subgroups. Good. I'm interested in finite groups. So, yep. With abelian quotients. Okay, fine. A group is solvable if there is a finite filtration with abelian quotients on G. Set up abelian group quotients if yeah, each one is normal. Okay, so we've seen that. What were normal subgroups? Normal subgroups was something to do with extensions over. Wait, do we have normal? We had normal extensions, right? Was that the link? No, normal subgroups were linked to. There was this really good bit a while ago. Normal. These intermediate things. Intermediate ones, right? M over K was a Galois extension if and only if that Galois group over the intermediate field is a normal subgroup. So this kind of link between normal subgroups and intermediate fields hiding in there. Okay, back down here. So we're thinking about normal subgroups, a sequence of normal subgroups, a finite filtration of G. It's a finite series of subgroups such that each is normal in the previous one. That is what we want in order to construct these intermediate fields. Number n is called the length of the finite filtration, fine. No redundancies, we don't repeat them, fine. Abelian quotients, if the quotient group is a abelian group, is that going to mean that it's really straightforward? Abelian quotients. Okay. Well, okay, that's what solvable is. If there's a finite filtration with abelian quotients, if that exists. Does that exist? If so, it's called solvable. And then simple if it's got no non-trivial normal subgroups. So simple groups will be ones where you can't do this at all, right? Or if it's only got the chain that goes from 0 to G. There's nothing in between. So just where here's 0, I think 0 means the group with one element, which is a bit odd, but hey. Which is sort of, it's G0 here is a normal subgroup, so I'm asserting that it's the group with one element. Okay, here's a lemma. If G is a solvable group and H be a subgroup, then H is solvable. Right. If H is normal in G, then the quotient group is also solvable. Oh, that's exciting. Should write the group operation on G multiplicatively. Take your finite filtration without abelian quotients. So solvable means we've got abelian quotients, good. Remember that. G star be a finite filtration with abelian quotients on G. M be the length of filtration. Though for all I in there, the group H intersect with GI is normal. Oh, okay, gosh, you just intersect it. Indeed, for any H, the automorphism. Go and look at this. Gi plus 1 sends H into H and Gi into Gi, and that sends H and Gi into H and Gi. Huh. Thus, you can just intersect each one with H. It's a finite filtration of H. Huh. Okay, just intersect it, dude. Furthermore, for all I in there, there's an injective map of groups. Injective map of groups. In you go. Such that this. Hence those are abelian as well. Okay, group maps. You want to do your quotient such that. Yeah, okay, so the way to do this quotienting on this, so just do the quotient on Gi, such all phi. Okay, phi, so all gamma, phi works like this. The place I would like you to take this gamma element of this thing quotiented by that is to just go to look up the group of gamma, the coset of gamma in Gi plus 1 under Gi. It's injective, it's a subset, it's abelian. Gi plus 1 and H is abelian. Finite filtration with abelian quotients for H, hence H is solvable. And then something more about the quotients. Sequence of subgroups going up with looking at the cosets of those groups, cosets of H. So it's like looking at the opposite. Instead of intersecting, it's like looking at not the bits that are in the normal subgroup, but the bits that are kind of not the cosets. Gamma T tau B in Gi. That map is a map of groups. And then, oh my goodness, group stuff. And then this is in Gi because those are normal. So you can go the other way, those are normal. So it's finite filtration. There's a subjection of groups. Okay. So that's the fairly gamma. Since Gi plus 1 over Gi is an abelian group by assumption, that's also abelian. And thus, that's finite filtration with abelian groups. Abelian questions. Crikey. That was a lot of group theory suddenly. 5.12 says if G is a group and H is a normal subgroup, then if H is solvable and G over H is solvable, then G is also solvable. And that's being left as an exercise. We're supposed to construct a filtration by gluing filtrations coming from G over H and H. Okay, I can kind of imagine that. If you can solve H, if it's solvable, and G quotient H is solvable. Yeah. You just solve it. So H just going to be here. So H is a normal subgroup. So can I take that as my first one, please? And then H is solvable. It's a bit cheeky. Yeah, hang on. So normal subgroup means that then G of H is solvable. So take the normal subgroup chain there for G over H down to 0. And I kind of want to change that back into a string of G's because that's there's a normal subgroup involved. Oh gosh, got to get good at normal subgroups. Right, okay. The exercise is constructive filtration. Right, okay, fine. And then down here, find a group in a P prime number. Suppose there is an N such that the size of the group is like this, then G is solvable. Okay. And we're going to do that by induction on N. It's called a P group. Clearly holds N at 0. Otherwise, right, okay, apparently we can just solve it. Action by conjugation. A map of groups. Yeah, okay, conjugation. By orbit stabilizer. Any first course in group theory. The orbits of G all have cardinality, a power of P. The orbit of the unit element is 1, so not everything. Yeah, okay, not everything. And that G0 is a fixed point of the action of G on G. By definition, it commutes with everything. So if it looks at the centre, let's grab that out. That's the important concept. I think the centre is a normal subgroup, which is not just the identity by some orbit stabilizer stuff. Okay, the group ZG is abelian and thus solvable. This is, I think, the fact that sometimes you can deduce that a group has non-trivial centre, which I should look up in a group theory course, I think. By definition, the group is abelian and thus solvable. Abelian groups are always solvable because you can just go straight down from that abelian group down to the identity and say the quotient is this abelian group, that's a normal subgroup. It's all fine. And a quotient group has cardinality k for some k, and thus by induction, go get them. By 5.12, you can glue them together and it's solvable. The length is kind of the length of the finite filtration. Necessarily finite because the length can't be larger than the size of G, and probably quite a bit less than that. Okay, length G, no redundancies. Yeah, you can put in no redundancies, otherwise it can get really long. Then for all I in there, the group is a cyclic group of prime order. So not just any abelian group. For a finite solvable group, those quotients are actually really simple. They're cyclic groups. Finite solvable groups actually have easy or basic or easy quotients. I'm going to put basic quotients. Let's put cyclic for a precision. Cyclic quotients. Huh. This seems good. The questions are abelian groups. I suppose it's not a prime order by the structure theorem. There it is again. Finite generated abelian groups. It's isomorphic to the direct finite direct sum of cyclic groups, which is order prime power. So we can include that proper non-trivial subgroup. Call such a subgroup H. Consider now the ascending sequence of subgroups of G, like that. Oh gosh, what were those? Oh, in the direct sum, so they're kind of independent in a way, so build it up one at a time. Q inverse of H. Group H is normal in there, since that's abelian. Oh, I don't know anymore. Okay, fine. Proof for another day, I think. Using finitely generated abelian groups as proof. Right. Non-zero simple group. Oh, okay, we've hit simple groups. And G dot be a finite filtration with no redundancies. Length G. Length G on G. For all I in there, they're actually non-zero. Oh, I suppose more generally that G is a finite group. What was it before? Spot the difference. Finite solvable group. So actually, finite groups, the quotients are pretty basic. They're simple. Okay. Simple. So the quotients don't have any normal subgroups. That's kind of weird. No redundancies. That's probably the key thing. Okay. Example. Abelian groups pretty solvable. S3 is solvable. Here's how to solve it. A3 lives inside S3 with quotient 2, and then that's got quotient 3. It's a normal subgroup, so you can get down like that. Group S4 is solvable. The groups A5 and S5 are not solvable. Group A5 is like simple, no interesting subgroups at all in between, and not abelian. and thus only has the trivial finite filtration. Yeah, okay. This implies that Sn is not solvable for Ln bigger than or equal to 5 because yeah, you've got subgroups. Okay, this felt like a lot of technical stuff that we need for the Quintic. We're getting close to the Quintic. We're now talking about S5, and we're talking about solvability. Being solvable is about having this chain of normal subgroups inside your group, and S5 doesn't do it. Well, it only does it in a trivial way. Other ones do this. Other groups do this. Like S3 seems quite nice. S2, it's abelian. S5, not doing that at all. Okay. Half an hour. I want to take some notes on this. Look at solvability by radicals. And I think we're good. Camera extensions are radical. Radical dude. Okay, let's take some notes on these group things, solvable groups. So 5.3, so 5.3.1 is solvable groups, and then there's this next bit, 5.3.2. 5.3.2 solvability by radicals. Let's go. Solvability by radicals. So I need solvable groups. So finite filtration of G is a finite extending sequence of subgroups between 0 and G, such that each one's normal in the next one. Right, finite filtration of G. All the way down here. Finite filtration of G. Finite filtration of G is a sequence of subgroups, I'm going to call them, G0, Gn, such that, like this, finite filtration Gn is G, each normal subgroup of the next. And what else do I want? I want to say something about these abelian quotients. Finite filtration, no, something about redundancy is fine. Abelian quotients, if those quotients are abelian. Might have abelian quotients. It's funny that we don't put a capital A on abelian, even though it's named after Abel. Abel, of the Abel Prize fame. What are we doing? So then a group is solvable if that exists. If so, the group is solvable. Hooray! Another word that starts with S. Splitting. What have we learned? Up here we had so many words that start with S to learn. Separable, simple, splitting, solvable. Those are the vocab words we learned today. Okay, great. Having a wonderful time. I feel like it's about to come together. I don't want to speak too fast, but you know. So there's the dilemmas about finding solvable groups within there, but I think I'm going to leave it for now and talk about how A5 doesn't do that. You can solve certain groups, but I really care about the fact that you can't solve A5, and that's just not too bad because you can't get started. Only has a trivial finite filtration, which is a fact about A5, so I guess that explains that. 60 elements are going to work out it doesn't have any good normal subgroups. Okay, solvability by radicals. Let's go. 40 minutes on the session, and I think we're getting there. Where are we? So solvability by radicals is this bit here for a definition, and then a page, and then we go, oh my goodness, we start getting some diagrams. I love a diagram. Okay, it starts getting good. It starts getting really good. Look at these diagrams. Whoa, loads of stuff. Okay, solvability by radicals is massive. Then we start solving cubic equations over here. So page 38 really, okay. 37, splitting field of this mad polynomial, good. Okay. Following diagram of field extensions, how far away are we from that? A couple of pages. Want to see that today. Why am I not quite going to make it to the Quintic in 40 minutes? I really want to make it just a tag. Not understand it, not done, but just tag gets the Quintic. 2 seconds. Wherever I clicked in the wrong place. Sorry. Okay. Radical extensions. Here we go. It's said to be radical if L over K. It's said to be radical if L is an extension like this, and there are natural numbers such that these alpha 1 to the n1 is in K, alpha 2 to the n2 is in K of alpha 1. Ooh, each work on the way up. Radical. So it's an extension like this where you're using like cube root of 2 or something, and each time you add something in is an nth root. Each thing you add is an nth root of something you already had. Plus you do like field extensions, so you add stuff, you multiply, you build all this other stuff along the way as well. Each time you're doing the proper extension, right? So to get to k alpha 1. Okay. There are natural numbers such. Each one you do is, these are radicals, they're nth roots. Good. You might get all of them or you might not. I don't mind. Okay. From the definition of, if out of m over l are radical extensions, then you can just keep going. Just keep putting stuff in. Common extensions are radical. What were they? Let's go and have one quick look at common extensions again. They were the roots of yeah. So this thing splits in K. So separable polynomial. Okay, it's Gauss extension called Kummer extension. Really not getting the way that this has to split in K and then we extend it to M. It already splits. I don't know what a splitting extension is. No, it's the A again. This one splits in K and then we go to here. So this is a splitting extension. We're throwing in the roots where we're throwing in the roots of numbers that are raised to the power of A, such that, right, okay. For the Kummer extension, we're throwing in all of them, I think, because that's the splitting extension. Possibly. Let L over K be a radical extension and J over L be a finite extension, such that the composed extension is Galois. Okay, then there's a field L prime intermediate between J and L, such that the extension L prime over K is Galois and radical. So somewhere in between. Somewhere in between, you can go from. So you did a radical extension, cool, and then you wanted to keep going a bit more up to get a Galois extension, which Galois extension meant that you were going for something that was over a separable polynomial, something normal over a separable polynomial. Trying to get up to that automorphism group, and what you what I wanted to do is just go a little bit, don't go all the way to J, just go to L prime, and you can do that retaining the idea of it being a radical extension, and also make it Galois, best of both worlds. Okay, how does this proof work? Check if we can see any ideas in the proof. Suppose there are natural numbers such that these, that's how you build it to get to L. Let G be this Galois group, because it's Galois over there. Be some permutations from the automorphism group. Note that for any I in here, sigma and G, we have this thing, because of multiplication being nice, like this. Since sigma of this K stuff, some K of O, just permute the roots. Conclude the extension is also radical. Okay, so where are we going? We're taking in the alpha 1 up to alpha K, and then we're going to keep going. So we stop to K. Look for any I in here. Oh, there exist these natural numbers up to K. So that's why we're using K, not N, because we're using N for the actual natural numbers. Actual natural numbers. Conclude the extension where you get to K. So you take your roots up to alpha K, take your roots, and then also permute the roots under, oh gosh, each of them. Sigma T. Is T like the number of them or something? Take all of them? Oh, which is the orbit. Okay, the orbit of alpha 1 and the orbit of alpha K is also a radical extension of K. My goodness. I'm just going to construct a massive radical extension. Each of those things apparently is, yeah, I guess this is them checking that it's in the nth root of. It's in this previous stuff. It's in that, so it's in this larger extension as well. So if you have, you do your sigma 1 first, and it's, yeah, okay. Each of those, and the alphas are there, so then you throw in the sigma 1s. You can do the sigma 2s because your alpha's there as well. Your alphas, okay, your alpha, put the alphas in first now. These things. Okay, with the sigma, so you do this for each of them, right? For each of them, they are. It's kind of like using the sigmas, right? So in the extension with those ones. Yeah, because it's the nth power. Oh yeah, okay, so this nth power is in that extension. So sigma of AI, but sigma of AI is clearly, oh, this is the next one. We do them one at a time. Put them in one at a time. Why is it in there? Sigma, so why is sigma of alpha I? Why is that one in there? So sigma of permutation of this previous extension. Such that these Galois sigma T. Oh, sigma T was how many of them there are. In a way, let's, for any I in there, any sigma and G, we have this sigma permutation. It's applied to K, this alpha 1 to alpha I minus 1. For any I up to there, why would that be in that permutation? Let's put an exclamation mark there and come back. Conclude the extension where you just do them all. Like look at the orbits under all of these permutations. It's also a radical extension. You just build them one at a time apparently. Since that is, oh my goodness, for any sigma and G, we see that, oh my goodness, is a Galois extension. Ooh, bit much. We may thus let L prime be, and there's a formula for it down the bottom there. Just look at the extension where you look at the orbits of the alphas under the sigma permutations, using that under the Galois group, because J over K is Galois. Ooh, okay. Oh, here we go. Here's some good theorem. Character of K0, but L over K be a finite Galois extension. This is like exactly what the sort of thing I care about. Part A, if Galois of L over K is solvable with so much theory, then there exists a finite extension M over L with the following properties. Post extension is Galois. There's a map of K extensions to M, and M is generated by the images of L and K and M. Scrabble on the mountain. Extension is a composition of Kummer extensions. In particular, it's radical extension. And conversely, oh gosh, Gal of L over K is solvable. Wow, there's a lot going on here. Exists in Galois extension of K and maps of K extensions. Yeah, okay. Diagram of field extensions. You could go from L up to K, up to L, and then up to J, or you could go from K up to K, expanded with the roots of unity, called D, and then go to J. Oh my goodness. Let P be a field be generated by L and those. Now note P up to K up to P is a Galois extension. Because you can go via those ones. Yeah, I'm not getting much out of this anymore. What a lot of stuff. It's the only thing I've got. So it's talking about solvable Galois groups now. So this is exactly what we came for. So what we came for. If the Galois group is solvable, then there's a finite extension of the following properties. This thing's Galois. That's exactly the thing I care about. Here's theorem 5.18. I really care about characteristic K being 0. Extend up to L. Finite Galois extension. If Galois L over K is solvable, there's a finite extension to make it Galois. L over K was already Galois. Why are we extending to M? Oh, it's got loads of following properties. Loads of properties. Okay, multiple properties. Map of K extensions. K with the, what are those? Roots of unity over the extension you already had to M. M is generated, so it's kind of like roots of x to the n. It's generated by the images of L and K of the roots of unity in M. So M is sort of a bigger thing that's generated, and it's got it's a radical extension. It's a radical extension when made of a composition of these Kummer extensions. Okay. Conversely, you could go further to M such that it's radical. That seems to be the point of what we're doing here, to make it a radical extension. If the Galois group is solvable, then you can go a bit further. You can extend further to a radical extension. When you just built it out of nth roots, and this is going to be back to the thing about the finite thing, abelian quotients, cyclic groups. If your thing's solvable, be it solvable groups have cyclic quotients. So maybe that's why we're going to be able to turn those cyclic quotients into Kummer extensions, and then make that a radical extension, so that along the way our solvable group was just doing radical extensions. Okay. I'm not reading the proof right now. It's got some cool diagrams in. Down here. No, we're still going proof B. The proof is like 2 pages. This is strong. and down there finally it gets down to a proof stop. So now we get the definition. We say P of x is solvable radicals if there's an extension from M over L such that the composed extension M over K is radical. Splitting extension for P. So P is solvable by radicals. So splitting extension goes to include all the roots of P in some sort of sense. P is solvable by radicals if there's an extension M over L such that the composed extension is radical. The extension is radical. Okay. So solvable by radicals is going to mean that there's an extension such that the composed extension M over K is radical. And since all the splitting fields of P are isomorphic as K extension, doesn't depend on our choice of splitting field for P. Gosh. They're all isomorphic as K extensions. It's like choice of ordering the roots or something. But the previous theorem, P of x is solvable by radicals if and only if the Galois group is solvable. Right, okay, solvable by radicals for the polynomial means that, so this is the thing I've been saying about quintics all the way through. Here's solvable by radicals, and it's to do with extensions such that the composed extension M over K is radical. Why are we composing the extension with anything? So we go to the splitting extension to look at the roots. Can you solve that by radicals? So in order to solve it by radicals, you might need to throw in some more stuff. You might need to extend further. Which is okay. Well, okay, I'll allow you to extend a bit further, such that the composed extension overall is radical. You've gone to this huge field, which includes like these radical roots of x the n is something you already had. So I suppose this is huge, right? Because you could go L over K might be, the splitting extension might not have been that big, but then we'll say it's solved by radicals. If okay, fine, we can go and generate some crazy number of M over K. That's your formula, if you like. Your formula is going to be some generation where as you're calculating the roots using your formula, what you're doing is you're doing addition, multiplication, subtraction, fine, and division, field stuff, not divided by zero, fields stuff. Occasionally you take an nth root, and that's like moving to the next extension in this like chain of things in the radical extension. So as you're doing this calculation, you're finding something that is within some enormous radical extension, where the formula says you do this many, like square it, multiply it, take the nth roots. But for a given polynomial, that calculation that you're doing is going to lie inside this radical extension. So we said that P is solvable by radicals if you can extend it so that these roots that we're talking about lie within this enormous radical extension where you did all these nth roots and things. And theorem 5.18 has maybe demonstrated that P of x is solvable by radicals if and only if that group is solvable. That's what I'm looking for. That's the thing we're looking for, gang. Theorem 5.18. So this thing with the 2-page proof, we've got all the way. It's Mount Doom. Wait, it's given from here. This thing with a 2-page proof down here. So theorem 5.18. The proof starts here, has a diagram. First diagram, of course, has an entire page with another diagram, and then a bit more. So it's kind of 2 pages of proof. That is what we need to understand eventually this week, because that is the proof that P of x is solvable if and only if the Galois group is solvable. And the Galois group is going to be not solvable for some of these. Here's 5.19. The extension from K on n objects. I don't really know why there's n of them here, but hey, over the things fixed by Sn. So the things fixed by Sn is The ones, oh, because you work with the coefficients. So in terms of the coefficients means in terms of the symmetric functions. In terms of the symmetric, what's a symmetric function? It's something that's fixed by the symmetry group. So okay, it's the extension of all stuff working with the coefficients. Can you find the roots? So working with the coefficients that's down here, not radical because, yeah, and this is going to be because of the A5 thing. Okay, so that extension, why have we got so many x's? Are they the roots? I feel like they're coefficients. I don't quite get why there's so many x's inside here. I'm getting close to a quintic. Okay, so consider the action of Sn on that, which is the action induced by the action of Sn on the polynomials. Is that the field of fractions suddenly? Yeah, I think these are fields of fractions. Action induced by the action of Sn on the polynomials. Any ring automorphism of a domain includes an automorphism of its field of fractions from like 2.1 ages ago. And there's an action of Sn on that. So the stuff we were doing back in section 2 talking about symmetric stuff is relevant now because I now realise the symmetric functions precisely correspond to their coefficients. So if you're trying to do something only using coefficients of your polynomial, then you're really acting with the symmetric functions of the roots. So if those are the roots, if these x's, well, you call them x's, but if these are the roots maybe, then field of fractions, because you can combine them together and you're allowed to divide. You can divide by 2a. You're allowed to divide symmetric functions. Cool, okay. So, here's a proof. Oh, thanks for the follow. We're getting there. We're really getting there. We've got, I'm supposed to shout out the names, right? Tracteur Bibou. Thanks for the follow. We're getting there. The extension is a Galois extension by Arthur's lemma, which is like section 4. I've forgotten this already. On the other hand, so the action, end of the subsection that's not solvable. Yeah, I remember that. By theorem 5.18, the big one. This thing cannot be radical. Okay. So 5.18 is the kind of big linchpin that's going to help me understand why solvable by radicals is such a sort of big deal, and why it's something to do with solvable Galois groups. Let's go into the notes. Kind of stopped doing notes about an hour ago. 5.18 is like solvable versus solvable. It's how I understand solvable. And 2, please pay attention to section 2. Symmetric functions are the coefficients. Silly. The things you care about, the coefficients, the things that you're trying to put in your formula for the quintic. Okay, there. Okay, down at the bottom here. So, what is this note? Note that the extension is the splitting field of the polynomial. Oh, this is telling me, yeah, there's a relationship here. Indeed, the elements are all of the roots of un of x, this polynomial. So if you show me this polynomial, further, the elements xn generate k over k, and hence over this. Give another proof of the fact that it's Galois extension. I don't get it, but this is the relationship I wanted, that these symmetric functions of the roots. Indeed, the elements are all the roots of un. Yep, okay, good. Before theorem 2.16. So near before theorem 2.16 is very important near the end. So let's go before theorem 2.16 comes up later. Okay, that's my note to self at the end there. Okay, so this can be radical. So I've got a big job this week to try and understand the 2-page proof of theorem 5.18. In order to get there, I'm going to need to get much better at field extensions, Galois extensions in particular. I'm going to need to think about automorphisms and the strings of quotient groups. So I might go back and learn some quotient theory. Oh, would that follow from the tracteur Bibou? I've reached 2 to the power of 5 subscribers. It's a prime power, which means that there's a field of that order. It means that any group of that order is solvable. Right, okay. Did you get much experience in algebra? Yeah, I did. So as a student, I didn't do this sort of thing. That's why I want to do it now. I feel like I missed out. I did some of it. So rings yesterday, that rings a bell. It reminds me of some stuff I did, but I opted out of doing this kind of algebra maybe too early and missed out on some cool stuff. This kind of algebra and the group theory stuff, I thought I remembered, but I didn't remember enough. So I did a first course in group theory, oh gosh, more than 10 years ago, at the start of university. Everyone does in most university courses that I've seen. First course in group theory, just have to. And I haven't worked on it since. So I'm finding the quotient group stuff really quite difficult. And it's annoying because I feel like I shouldn't find it difficult, but I do. So possibly later this week, I need to schedule myself some time to get happier about these kind of normal subgroup stuff, chains of normal subgroups, and flipping between those normal subgroups and backwards and forwards. Like for example, in here, I just know that not this orbit stuff. These things, flipping between the group and its quotients. So this sort of thing. Group is normal in I just feel like I should be better at this sort of thing, working with normal subgroups and their quotients, flipping between them. I tried to think through the exercise over here to construct a finite filtration. I couldn't, and that annoyed me. So I need to get better at group theory, which is like the intro stuff that maybe this live stream should have started with group theory and vector spaces, rather than saying, I'll be fine, we'll just jump straight in with rings. Okay, we're down here. We're going to have a quick look at the next page because I think we've earned it. It's 10 to 5. We're going to look at some stuff. We're going to solve a cubic equation. Here's an equivalent equation for it. Good. Where this is that and Q is that, these things in terms of the roots. Fine. Okay. To do this, kind of change of variables to simplify it a little bit. Okay. We want to find a formula for the roots of P of X of the following form. So start with the elements P, Q, and which are rational. Oh, K is a field. I'm going to say K is Q because I'm lazy. Theorem 5.18 in a specific situation. That's what I need, I suppose. Only involve iteration of the following operations: multiplication of elements by elements of K, and extraction of second and third roots. Okay, we're limited it, right? That's what our formula should do. Right, okay, we are splitting extension for P of X. Let omega be the primitive a primitive third root of unity, which is either of them that aren't one. Okay, in C. No, 3 is prime. This is always true. Either of them that aren't one. It generalizes nicely. Existence of splitting extensions. Construct a finite Galois extension J over K that maps of K extensions. What is going on? What is going on? Invoke the lemma. Ah, today has not been as successful as yesterday. We're still getting through things. We're just trying to work out what on earth is going on. The field generated in J by the images of L and the field of fractions of those. Wait, I'm saying field of fractions again when I just mean field extension. Did I do that a little bit over here as well? No, yeah, those are field of fractions, right? Are those numbers? No, this really was a field of fractions. Okay, good. I'm finding the round brackets quite confusing. Right, okay, so extension where you go to the situation is summarized in the following commutative diagram of field extensions. Okay, so from K, you could throw in the cube roots, which is generated by a primitive one. You could do that, or you could go up to L, or you could go up to L with omega in it as well. And either way, you end up at L of omega. L, sorry, augmented with omega. Maybe you did K augmented with omega first, and then you changed K up to L. That's M up here. What's J? Where's J living? Finite Galois extension. J over K. The maps. Okay, I need to relearn what splitting extensions are, I think. Not proud of that. Really felt like I'd learned them at one point today, but going back, okay, relearn what splitting extensions are. Construct a finite, okay, there's J. Right, and such a diagram is considered in proof of theorem 5.18. Okay, there was a diagram like that, I think. Since the Galois group is a solvable group, because it can be realised as a subgroup of S3, this is good. Not very practical. It's not totally, because we've left P and Q behind, but hey. The argument given in the proof of theorem 5.18 actually shows that M over K is radical. M over K is radical. So play through down here, this extension, to get right up to M. It's radical. Oh, yeah, okay, so because 5.18 was all about solvable groups, meaning that it's kind of built out of cyclic things, and the cyclic things correspond to radical extensions. The calculators below exploit and reprove precisely this fact. Good. Okay, I would like that, please. 5 minutes. Consider the sequence of extensions. K goes to K omega, then go up to omega with the square root of the discriminant of M. Any, by definition of any square root of that is a polynomial in the roots of Px, therefore lies in any square root of that is a polynomial? Oh, in the roots of Px, and therefore lies in L. Oh, it has a square root, because in the squares. Yeah, you're supposed to think of positive real number or something. Okay. Goes up to M. Right, okay, if the discriminant is a square, which we said was something like that, corresponding to that being in the AN group. Anyway, note that proposition 5.4 ages ago. Quick look. The map is surjective if and only if it's irreducible. Oop. It's a quick look. The thing is less than or equal to 2. The degree of that extension. Oh goodness. One more look at 5.5. 5.4 is because omega satisfies quite a small polynomial. Nope. Injection. Oh, there's an injection from it. Oh, I should take it more slowly. Anyway, and that this thing extending like that is less than or equal to 2. There is a polynomial that this satisfies some pretty nice polynomial square of this is supposed to be in K. The square of this is just W, so it's just in K. Good. So that degree is pretty small as well. Note also that M is a splitting field of P of X over K, and that by construction. Again, splitting field, fine. That's using 4.7. We see that a Galois group can be realised as a subgroup of A3. Ooh. But A3 doesn't have very many subgroups, does it? It's just, yeah, no, it's tiny. It's only got 3 elements. Lemma 4.7, part 4. What's lemma 4.7? Looking at 4.7. Part 4. The image of phi lies in AN, if it's a square. Okay. Oh, this is the thing to say that lies in AN. Okay, it lies in AN. So it's a group of A3, which only got 3 elements. So it's either the trivial group for the extension of M over K with these things, trivial group, or the group with 3 elements. Now let alpha 1, alpha 2, alpha 3 be the roots of Px with multiplicities. Let beta be like this, and let gamma be like that. Oh, that's nice. Those look like the things from, oh gosh, the beta calculation that we had, which I didn't understand what it was for. Note that these things add to 0 because that's the coefficient of x squared in the new polynomial, and in particular we know what alpha 1 is and alpha 2 is, alpha 3 is. We've plugged in our values of beta and gamma from the definition of the polynomial over here. P and Q? Yeah, no. I'm going to keep going. I'm live, it's 5. I'm going to keep going, I want to understand this a bit more. Similar reasoning. Alpha 1 is 1/3 of beta plus gamma. Where's that come from? Alpha 1 plus alpha 2 plus alpha 3 is 0. Is beta and gamma in M? Similar reasoning. Alpha 2. Beta plus gamma. Oh, if you start adding these things together, then you get here minus alpha 2. No. Yeah, if you add these together with, if you add all 3 of these equations together, you get 3 alpha 1s, you get no alpha 2s, you get no alpha 3s, you get beta plus gamma on the other side. And if you multiply and rotate, then you do some rotation, and you multiply up, then you can get equations for alpha 2 and alpha 3. Oh, so these are the roots in terms of beta and gamma. Wait, these are the roots? No. Yeah, these are the roots in terms of beta and gamma. Beta and gamma. We don't have beta and gamma in terms of P and Q yet. But these are pretty nice. These are things that lie in M. Okay. Now we claim that beta cubed and gamma cubed lie in this. If that's the trivial group, then this holds just fine, because M is actually equal to that. Beta cubed and gamma cubed definitely lie in M, so they would lie in that as well. If the gamma group is lemma 3z, then the claim follows from theorem 5.7 and lemma 4.6. Oh gosh, so many numbers. Note that in this case, Px is irreducible and the roots have no multiplicities. That sounds like Eisenstein's thing, and check P prime and P for the no multiplicities. So we see the minimal polynomials of b cubed and gamma cubed over k are of degree less than or equal to 2. So satisfy quadratic equations, coefficients in k of omega, k extended with omega. In turn, the elements of k of omega satisfy quadratic equations with coefficients in k. That's express alpha 1, alpha 2, and alpha 3 by formula involving only multiplications, additions, and subtractions of second and third roots. Make this explicit. Please do. Let's go. So compute beta gamma. Note also that, oh gosh, yeah, that's 0 squared. Okay, Thus, beta gamma is this thing minus all of that squared, which, oh right, okay, so that's going to get rid of loads of these terms, which is minus 3p. And similarly, we compute this term. I don't know where these are coming from, but these look like sort of symmetric things. Right, we're going to work out the beta gamma cubed are roots of the quadratic equation. Ooh! Oh, beta cubed and gamma cubes have... Okay, so they lie in here, so you can go get them. Yeah, we're working out the cubic formula. Hey, a cool person. We're getting the cubic formula. So the idea of the beta cubed and gamma cubes lie in this particular field extension. And actually, you can work out where they are in this field extension, I think. I think that's what's going on. So if here we work out that beta cubed gamma cubed is equal to 27p cubed. So we're starting to piece together this like quadratic equation. Extract those. So we know that up here we worked out that there was a quadratic involved. The minimal polynomials of these things. In fact, that the roots of this shared quadratic down here a degree bigger, at least a degree at most 2 quadratic equations with coefficients in k of omega. But those satisfy quadratic equations with coefficients in k. So it's kind of like building the structure, right? You go from k to k of omega to k of omega with beta and this thing up here, square root of the discriminant. The square root of the discriminant gives you enough to say, aha, we're in there. Galois the if this Galois group is the trivial group, then M is, which is fine. You can definitely extract the cube roots from here. Well, you can extract beta cubed and gamma cubed and then do the cube root thing as an extra kind of extension towards the end. Maybe? Yeah, okay. So putting it all together, you get out to here. And the thing is, you can do that without saying any of the Galois theory. You can just kind of work out that these things exist and say, oh, brilliant, okay, I've just realised magically that beta cubed and gamma cubed happen to obey this quadratic equation, and I've gone and worked out what quadratic equation it is. The kind of good thing is that there is such a quadratic equation. Backtrack a tiny bit. So beta and gamma, these things. So I want to understand what these things are in general, I suppose. So those things look a bit like the ones that we calculated. Okay, beta and gamma play an important role here. And previously we saw things that looked a bit like that with roots of unity. Not obviously you have to do it like this, but Quintic's going to be a separate. Quintic's going to be a separate mountain to climb. Actually shows that MOVK is radical. So you get to MOVK. Yeah, okay, so theorem 5.18 did this in one way, and then the calculation below is checking it for this particular case. Yeah, here, these things, these degrees, at most 2. That's like saying that that's where the quadratics are, maybe? Subgroup of A3. From previously in the lecture notes, that's a subgroup of 4.7. Either the trivial group or that. And then in here further down, what was that Galois group? It's part of A3, so we're kind of exploiting the fact that you can, that somewhere in there's a solvable group, because A3 is fine. And then the idea from 5.18 is that this turns out to give you like a radical extension, because solvable groups have cyclic abelian quotients. I think that's my kind of like vague impression so far. Got to dig more into 5.18. Solvable groups have, I think solvable groups have cyclic abelian quotients on their finite filtration. Oof. This one's solvable, so hey, we can do some radical extension, and then this calculation explicitly goes and does it, which, fine, but the expression at the end is totally mad if you put everything together. Those are the solutions. Wait, there's beta 1? Why are we calling them beta 1? I don't love that. Beta is something different, right, to beta 1. And there are 2 more. Yeah, here are the other 2. For some choices of third roots, not all of them will give solutions. What? Here we're doing it over a general P and Q. Not all of them will give solutions. We've seen some sort of things where you can't assume the converses along the way. In these calculations, P and Q, you've also got to calculate along the way as well. Actually valid more generally, as long as the characteristic's not 2 or 3. The thing is, you don't really need to know this maths. The idea here is, well, so the idea is that there's a big chunk of Galois theory over here that justifies the idea that beta cubed and gamma cubed, with quite basic objects, satisfy this nice quadratic equation. This quadratic equation's got 1 capital X and 1 lowercase x. I don't love that. I'm going to go with lowercase x. There's some quite nice quadratic equation that's satisfied by beta cubed and gamma cubed, where those things are just something to do with you can plug those into the roots if you extract cube roots, and with some extra spice of roots of unity. So if you know about complex numbers, you can do the calculations. I could snip out the Galois theory bits of these 2 pages and just show you the calculations, and it would look totally magic this way that you get to decide to look for a quadratic equation for beta cubed and gamma cubed, these kind of combinations of the roots. The algebra looks kind of weird. It says take the 3 roots in this cubic. The sums of the roots, when you combine them with the roots of unity stirring around, you could make these other things, beta and gamma. They satisfy this really nice quadratic. We're going to solve the quadratic and then come back and do the cube roots. That's not very satisfying. The idea of Galois theory is trying to understand this a bit better, understand why this works. Say, wow, we had a quadratic at all. If you could do something like this for quintics, to say, aha, I took your roots, I combined them into beta, gamma, delta, and epsilon using more Greek letters, and then I stirred those together and found, hey, they satisfy this really nice quadratic equation or something. So just go and solve for those, and then you'll know them, and you can invert my mixing thing to turn them back into the roots of the equation. If you could do something like that with the quintic, then you could get a formula for quintics. The idea is maybe that if you understand the Galois theory, you'll understand why you can't. So for a long time, people tried to do this kind of clever messing around with. You take the roots, you don't know the roots, but you take the roots and you do combinations of them like this up here, combinations with roots of unity to make these beta and gamma ideas. I kind of like mixing around, from which you can re-extract the roots. For years, people tried to do that in such a way, and then find equations for these new objects such that they turned into nice equations at the end, like a quadratic or just something involving like maybe the cubic formula. Now that we've got the cubic, it would be nice if the next time around they turned out to be the cubic and we could extract them from these cubic square roots and cubic things, maybe like by induction or something. But there's no induction here because the groups get worse along the way. Behind the scenes, the reason we got away with this is that these things have got quite small degree, and these radical extensions somehow, in a way I still don't understand, corresponds to solvable groups. Solvable by radicals means something to do with solvable groups. Solvable groups turn out to have pretty straightforward finite filtrations with abelian quotients, and that only works. You can only pull that off. Solvable by radicals means something pretty special about your group. You can only pull that off for small groups. If things get too complicated, too mixed up, then you can't get back to the roots using this kind of radicals. Okay, in here somewhere, skimming through the next page, we've got some group facts. Do I want these? Any second course on finite group theory is so funny to me. Any second course. It's like, I've seen the phrase see any course on group theory, right? See any first course on group theory. It's like, no, that's pretty basic. You just see it in any first course. The admission in this statement that you have to look at a second course is like, where did I leave my keys? The second place you looked for them, right? Not the first place. Brilliant. Okay. So there are some groups. If your group's got this size, then you can find subgroups like this. Brilliant stuff. And then kind of, I didn't commute the groups get together. Anyway, P silo subgroup. And then conjugate, that's the word. It's an element of order P and G. Brilliant, okay. But all of this is, I think, going to not work for S5. There's a cycle, one orbit of cardinality K in there. It's a K cycle. Okay, right. Yeah, it just cycles these with K. I think H prime is just a second subgroup in here. If H and H prime are in G are two subgroups, I think they're just two random different subgroups, well, both of which have size P to the n. And I'm not super jazzed by this. I'm kind of skimming it really fast because I think none of this is what's going on. Or maybe this helps us break down some symmetry groups or something. Like in here, an orbit of cardinality 1, fixed points. Okay, a K cycle necessarily has order K. Well, you do it K times, right? Orbit of cardinality. The K thing's in there. I suppose, why is it not a factor of K? Fine, okay. Well, then it would be track the objects around. There wouldn't be one orbit. Anyway, transmission 2 cycle. P prime number, order of sigma is P, then sigma is a P cycle, sounds fine. Elementary group theory, brilliant. That P prime number, if these are in here, I suppose that is a transposition and T is a P cycle. Ooh, that is cool. So we can generate S5. That's quite good news, actually. Generate S5 with 1, 2, 3, 4, 5, and just switches. Yeah, okay. Huh. Do any symmetry like that? Fine. Okay, good. I vaguely remember that from group theory, and again, it's frustrating, but the stuff I should know from group theory, can't quite remember. Right, let P be a prime number, and let P of X be an irreducible polynomial to P. Suppose that, here we go. Suppose that P of X has precisely P minus 2 real roots in C. Almost all its roots in C. Wait. Wouldn't it have repeated roots? No. Oh, P minus 2 real roots. Come on, James. So exactly P minus 2 real roots. It's an irreducible polynomial of degree P. Is it monic? Maybe, maybe not. I mean, it's got almost all its roots. Almost all its roots are real. Okay, here's the proof. 6.5. I'll scroll up a tiny bit. There's the Quintic. L of a cube is splitting fields, so once again I've got to get better at splitting fields. We identify L with the field generated over Q by the roots of P of X in C. See the remark after 3.13. The roots of P are distinct since P is separable. Look back at 3.6. Choosing a labelling of the roots, we may view Galois group, the extension of L over K, as a subgroup of SP. It's going to commute those. Since P of X is irreducible, the ring is a field, and there is a map of Q. Oh, no. Since P is irreducible, the ring is a field. Can't imagine that ring at all, actually. So it's ring questioned by the ideal generated by P of X. So start with P of X. Generate me an ideal. Why would that be a field? Q of X. That's polynomials. Polynomials do not form a field, do they? Degree really small or something? No. Q of X question with P of X doesn't look like a field at all. Anyway, moving on. There's a map of Q extensions into L. So P divides L over K. Oh, degree of the extension. Polynomial of degree P. P prime. Irreducible polynomial of degree P. Okay, for example, 5. What do we want? Doesn't look like a field to me. Qx over Px. Ideal generated by P of X. Does not look like a field. I'm being shallow-minded, right? Because polynomials questioned by polynomial can be isomorphic to a field, like could be isomorphic to C or something. So I think I'm being shallow-minded, and I need to loosen up a tiny bit. Yeah, okay, this is again, so if P is irreducible, then this ideal that's been generated is maximal. This is some sort of UFD stuff, right? Here we go. Whoa, rings from yesterday. P is irreducible, so this, yeah, it doesn't look like a field, but it's isomorphic to a field. It looks like a bunch of polynomials and how you're going to divide by those, but sometimes the thing you generate can look like the complex numbers or something. So I've got to be a bit more open-minded about what fields look like. I've got weird multiplication rules in here because of the quotient. That ideal is maximal or prime or something, which means that this is a field, one of those things. And so, okay, there's a map of Q extensions. I've got past a little bit here. Q over P goes to L. Roots generated. Okay, Q extensions from that field up to L. Since the size of the Galois group is the degree of the extension, P divides the size of the Galois group. Okay, so Galois group. Okay, P divides the size of the Galois group, but the Galois group is going to be a subgroup of SP. Right. Okay, that limits it. So now group theory. Cauchy's theorem. There is an element sigma of order P in that Galois group. P divides the order. Okay, so there's an element of sigma of order P. From lemma 6.3, we conclude that sigma is a P cycle of SP. It's kind of building up. On the other hand, note that complex conjugation is a field automorphism of C. It's complex conjugation. It's coming right at the end. Here it is. Since L extension of Q is a Galois extension, we see that the image of L, before spot that, image of L under complex conjugation is again L. Why does it matter? There's a Galois theorem. Once again, look at theorem 3.13. Have I already got a note that theorem 3.13 is a thing I need to learn tomorrow? Yeah. Including the note afterwards. Okay, back in. Hence it restricts to an element kappa of Gal L over Q, we have that one is not the identity element, since P of x has non-real roots by assumption. Yeah, complex conjugation doesn't just keep you still. So let alpha and beta in L be the two non-real roots. Then we must have kappa of alpha is beta. They must switch them backwards and forwards. In particular, kappa is as a transposition in SP. So it's going to generate all of SP. So the Galois group is SP. And now we hit a polynomial of degree 5 down the bottom. And it's irreducible. So it's going to meet the things that we need for 6.5 up here. 5 is prime. And then we'll go to some effort to check that it's got exactly 2 roots in R. So it's of the sort where the Galois group definitely contains transposition corresponding to complex conjugation, and definitely contains cycle because it's got an element of order 5. Group theory does matter. 5 divides the degree. Okay, anyway, it turns out the Galois group associated with this polynomial for the extension of the rationals to the field containing the roots of the polynomial is S5. But S5 is not solvable. So P of x can't be solved by radicals by theorem 5.18. Okay. There's the Quintic. That's the thing we're questing for. We got here for the first time. We pushed through things that we didn't understand very well at all. Pushed through, and the main feels like there are some barriers, but we've got a better idea of where those barriers are now. I really want to, just before I call it a day, double check what so that my barriers, I think, are splitting fields. Splitting fields have really let me down a little bit. I thought I had a good sense of them earlier on. I'm going to quickly check my notes for splitting fields to see what I had. And then splitting fields. I thought I understood them, and then they just turned up more than I was expecting. And they were up here somewhere. And normal fields, normal things didn't come back. Oh, Galois things were normal. A splitting extension for P of x splits in M, and then it's generated by the roots of P. Okay, so it's precisely the one that's generated by the roots. Generated by the roots, and it then splits in M. So generated by the roots of P, and it splits in M. Polynomial splits if you could just factorize it nicely into its roots, which you can do in M, where you have the roots. Okay, got to understand that better. Okay, so let L over Q be a splitting field for P of x. That means then, over here, that means the field generated by the roots of P, in which the polynomial splits, because you could now factorize it in terms of those roots that live in there. Okay, identify L with the field generated over Q. It's a field over Q because you've still got Q around. Yep. The roots of P of x in C. The whole thing lies in C. I guess that's what J was for us in a way. The roots of P are distinct since P is separable. Okay. Stuff from 3.6 is around there as well. So a quick look at 3.13 because I feel like that was a bit of a barrier. There exists a field extension. And splitting extensions as well. The definition of a splitting extension. Okay, so given P in a polynomial, there exists a field extension which is a splitting extension for P. If L over K is a splitting extension for P, an element of isomorphic, there's kind of only one way to do it. Put the roots in. L over K, the isomorphism is not just literally 1 to 1. You can mean them, I think. I don't really know what canonical means. Okay, there's a barrier there. Let L over K be a splitting extension for P, and let J over K be any K extension. The images of all the maps. The images are always, yeah, this was one of the things where I thought it was, what are the images? Images of all the maps from L to J coincide. So you've got J be any K extension. You've got to think about what you're doing with the images of the roots. Okay, 3.13.3 is really important because these images, in terms of automorphism, if L and J are the same thing, so if you do your splitting extension and then you look at the maps from L to itself, those automorphisms form the Galois group. So when the images coincide with the identity map, so they're all surjections onto for the whole thing. Back in here, where do we need to use 3.13? So this is now what my life is going to be like for a bit. Flipping between different pages, trying to compare what we were doing back there and what we're doing over here. We've got the marsh now. Okay. How are we going to be successful on our journey? Since L gives a Galois extension, we see the image of L under complication is again L. So I think this is saying the image of L is always going to be L because the images of these automorphisms are always the same as each other. It's the same as the identity automorphism, right? Maybe that's cheating. Restriction element kappa. Restricts to an element. So this element of the Galois group. Right, so the image is L, so fine, okay. So there's an element of the Galois group which corresponds to this particular field automorphism. Oh, it restricts down. It's a field automorphism of C, so it's also a field automorphism of L. So the automorphism there on C, technically it's only moving around some of the stuff when you start looking at the Galois extension of L over Q, because that's not all of C. Fine, okay. So this restriction is just this kind of thing to say, well, actually, complex conjugation applies to all the complex numbers, and here we're just restricting down to some that are in our problem. Phew. Okay. We've hit 5:30. I've been live for 4.5 hours with a 5-minute break, but you know, I think I want to call it a day there. I've got a kind of to-do list of things that I want to understand a lot better. In particular, I want to get quite a bit better at this group theory. Back to the map. Well, I think we always start and finish with the map, so let's go back to the map. Oh, we've seen so many maps today. So, what have we learned? We've learned that there's this classification of simple finite groups, which sort of says that if your group's solvable, do I need that for the Quintic? Here's the question. I'm thinking about drawing in a whole forest that goes round with simple finite groups. So classification of it's classification of abelian groups, finite abelian groups. Classification of finite abelian groups feels slightly relevant, like maybe for a proper understanding of Galois theory, you should probably pick that up along the way as well. And that came from the kind of rings down the river from the ring theory. We didn't do it yesterday, but down the river from the ring theory, this module stuff over here. We should have learned modules and then the classification of finite abelian groups. So if I want to properly understand what's going on in Galois theory, I'm going to pick that up as well. Okay, so over here, this group theory did involve some stuff about finding elements of order P, because we wanted to prove near the end, we wanted to prove that for that Quintic that the Galois group really was S5. I think I want to go at some point, if I was visualizing this for a YouTube video or something, I want to go and start showing what does S5 do to the roots of that polynomial. I mean, the roots are not that inaccessible, right? They're 3 real numbers and 2 complex numbers. So can we just plot them, please, and talk about those. Try and plot the field. I mean, the field's probably going to be dense in C, so it's going to be quite hard to look at. But can we look at maybe some examples of points moving around when you apply the automorphisms? See how the roots move to each other. And that might give more impression about how there's lots of ways to move the roots around according to S5, and you can permute them. Lots of ways to move them around, and in particular, it's going to be so hard to communicate this kind of radical extension thing. Solvable radicals. Yeah, if you could build a formula, and the formula would be built out of radical extensions. Radical extensions correspond to basically cyclic quotiented. This is the sort of thing we're going to do. Okay, so unfortunately, the quest's not over because we got a bit of a detour into group theory, and I think tomorrow it might be fun to do the group theory, to look at the group theory that's at the end of the Galois theory notes, and the kind of triumphant stuff about generating S5, to get really good at group theory, and also to think a little bit more about those quotients and finite abelian groups. So I think what we've discovered is that this forest over here is important. It kind of means that we need the help of the friendly elves over in the group theory forest. So I think tomorrow we're going to go over here and learn some group theory, get the help of the elves. So I think that's the plan for Wednesday. We've been and seen, we've mapped out what's going on in there. These radical extensions, fine, great. There's something to do with solvable groups. We want to get good at group theory. So I think in order to be able to do the last bit of the quest, to understand that stuff at the end, definitely want to get better at group theory. And then maybe Thursday, Friday, we've got time to come back into theorem 5.18, which is the big bit of theory where within theorem 5.18, all of the extensions that are going on in there, really understand splitting extensions, and be able to build a path. I guess that's what we're doing. The quest for the Quintic is not just about running up and seeing the word Quintic. It's also about getting out alive and surviving it. You can't just grab the idol and hope for the best. You've got to have an escape route. You've got to have a plan. I guess that's different from Lord of the Rings, where they just had to get there. They didn't have to explain to anybody else how to get there. I'd like to actually understand the journey that we're doing. I feel a bit like I've read Lord of the Rings word by word. Like I've looked at each word, oh my goodness, loads of words in the Lord of the Rings books. Looked at every single word, but I haven't really understood the story, right? I haven't really understood why they're doing things. Why didn't they just go be equals? I haven't understood how these things fit together. So the quest continues, because we might have speed run our way through the notes until we saw the word Quintic, but the quest continues because I don't understand that at all. I've got some ideas, but I'm going to need some help from group theory. So tomorrow we're back live at 9 AM again in this increasingly bizarre arts project of a live stream, where I'm going to do some group theory to try and get better at subgroups of the symmetric group, armed for that last bit of the quest, and then maybe some more slog through trying to understand radical extensions. I don't think that sounds fun. So that's not the best note to sign off on, but hey, look at my nice map. Right, as always, the quest is to be continued. Do we plan on taking brief detours to ruler and compasses? It's just sort of all this like nice stuff, these other mountains, right, over here that we could climb. I mean, other mountains. So if I'm honest, I want to really understand. I want to really understand Galois theory, which probably means understanding this like other stuff, and then that ruler and straight edge stuff. And Elrod, I know yesterday you were asking about the fundamental theorem of calculus. That's in these lecture notes. like it's on the next page. So if we want to understand the fundamental theorem of algebra, we kind of get that as a freebie at the end for understanding Galois theory. So we can do some cool stuff if we understood it properly. My kind of aim for the week is to understand Galois theory well enough that I could go and ready for that quest. But I'll accept if I only understand over fields of characteristic 0, where everything's either Q or C or R or something, then I'll accept that as understanding on my quest. Thanks, cool person. Quest continues starting tomorrow. Continuing tomorrow, because, like always, the quest is to be continued. Still not a good sign off.